is what you can do, then it works out. And the restriction, and I'm telling you this because this is going to be the type syntax that I'll be talking about. What you can do is you just have to restrict the types that are transmitted in messages. You have to restrict them to be closed with respect to recursion variables. This is actually, it's not really a restriction because, as Bernardine and Hennessy showed, you can just unfold your recursive types until they meet this restriction. But for now, actually, I'm not going to need duality in this talk. But just for now, I'm working with this subset, and I'm assuming this naive definition of duality. So according to Bernardine and Hennessy, and actually we looked at it also in some detail, this is fine. Well, so that's just an example for an interesting problem in connection with duality. So the one that I'm actually going for is about like the nature of the recursion. So how you approach recursion in a type system. And actually there are two basic approaches that I guess most of you are familiar with. So on the one hand, there is equi-recursion. And that's the idea that recursive types are just considered modulo unfolding. And this consideration, so this equation here is taken entirely silently. So whenever you need it, you just assume you're looking at the unfolding of the type, and whenever you need it differently, you can just fold it back. So they're considered equal. Some authors, I'm not sure, I don't see. I was thinking of Luca Padovani, but he isn't here. Some authors like to consider recursive types as the infinite unfolding. So your type is already an infinite object. The nice thing about that is you don't need any particular expression syntax. The downside is that if you're not careful, you need to do coinduction all the time, which is also tricky. Well, if you look at iso-recursion, then it looks like things are much simpler in a sense, because instead of having this silent equivalence, you have you just consider the recursive type and its unfolding as isomorphic. Yeah? And you actually have to exercise this isomorphism in typing, so there is explicit syntax for introduction and elimination. And you find that also, I mean, this is standard stuff from textbooks. You'll find it in the Pierce book, in Harper's book, and wherever you look. And the, oops. The interesting thing is, if you look at the literature on session types, you'll almost exclusively find them treated using equi-recursion. So if you have recursion in session types, I was only able to find one or maybe two papers that kind of had a hint of using iso-recursion at that point. All right. So here's an example why this is usually, well, why I think this is usually assumed. So the literature isn't really clear about it. So very rarely you find a half sentence that says something about it. Usually it's just tacitly assumed. Yeah, we'll add recursion and it's going to be equi-recursion. So here there are two session types. Well, this is kind of sending integers ad infinitum, and this is sending one integer and then another integer and then iterating that. Well, and if you consider that modulo unfolding, then these two types are equivalent. And this is, I already said that, this is actually the common case in session type theories, which means a server that assumes S1, and forgive me for being fuzzy at that point. I don't want to put too much formalism in here. So a server assuming S1 can communicate with a client that assumes the dual of S2. There you have it. That's why I showed you the definition of dual in front. Yeah, so the server looks like this. It just sends and recurses, and that's it. The client just receives things. Well, for the sake of argument, it prints something. Yeah, but essentially these are two loops, and you can easily sync them. So the server needs to do 2 iterations, and the client has to do 1. And things are fine, because the only thing that's ever happening on the communication wire is this send and receive actions. Well, what does it look like in the iso-recursive world? In that view, the two types are actually different. So they are, well, there are two syntactically different, and also according to the Iso-recursion theory, there are different types, which means a server assuming S1 cannot communicate with a client assuming the dual of S2. That will not work because, well, the server, the server obtains C in this recursive type. Well, on this recursive type, you cannot do any interesting action. You first have to explicitly unroll. So that's what's happening. Then you can do your action, and then you can recurse. Client, well, it has to unroll. Then it can do two actions before it has to unroll again. Well, and the thing is that this unroll has to, well, that's the assumption in the literature. This unroll has to synchronize. And if you look at other uses of recursive types, that's how it usually works. So if you look at recursive types, iso-recursive types in any other context, then you need this explicit roll and unroll thing. Now, so here the assumption is unroll is a synchronization operation. All right. However, well, the types look similar enough, and as equi-recursive types, they are even equivalent. We can actually interpose some adapter process that kind of mediates between the types. And I'm just showing you one of them. I guess any one of you can construct that, and it just performs the rolls, well, actually the unrolls on the right side of the world. So you can see here, there's one unroll of C2, which is S2, which had the two communications before it recurses, and you see two unrolls of C1, which has this single, the tighter loop in a sense. And if you put this process between the sender that we saw on the previous slide and the receiver and the client, then they will be able to communicate via this adapter process. Now the question is, of course, how do we obtain this process? And it turns out this is reasonably fine. What you do is you formally write down the definition of equi-recursive type equivalence, and that happens to be the same as a notion of compatibility between iso-recursive session types, and that's going to be a coinductive definition, usually. So, and I'm not going to show you the whole thing, just some key elements. Yeah, well, end is end, and if you are receiving something of type T, well, the types, the payload types, they have to be equivalent. At least their session type parts have to be equivalent. That's the definition of type equivalence here, and the continuation session also has to be equivalent. And the whole well, problems in a sense come in with these unrolling rules. So if you find a mu on one side, then you are allowed to unroll that. And that's a nice coinductive definition, and you can also show that it's productive and so on. So this defines a well-formed relation. And actually already Simon, where's Simon? Simon and Hole in their paper on subtyping for session types, I mean, they essentially used, well, they didn't write it as a rule system, but this is in effect, well, they defined a subtyping relation. But if you ignore the subtyping, this is like the relation. If you tweak it into an equivalence, this is more or less the relation that you would get. Okay, well, now you have this relation. Now what we need is, oh, I already put it in the title, the adapter witnesses this type equivalence. So we'd better be able, if I have a proof, well, a proof structure for such an equivalence judgment, then I would like to be able to extract the witness, actually a process that mediates from one equivalent type to the other. Okay, so we can do that. That's also fine. Well, obviously, somehow this is a process that has to connect a channel of type end with a channel of the type of the dual of that, right? Because we want to interpose things. I don't really want to go, well, anyway, so on one end you need to I don't even know which is which. So on one end you need to mediate a weight into a term. So one consumes the end question mark, and the other one produces an end blank, essentially. So here, this is probably easier to explain. So on the left, right, so on the left, we are receiving something of type T. Then here you have to interpose the equivalence of from T to U. That's like here, and then you send that out on the other channel, and there you go, that's like the implementation. And for the recursive parts, you just have to put the unroll operation on the right side. Now, wherever the recursion is, you have to do the unrolling. So that looks pretty cute, but unfortunately, it's unsatisfactory because if you look at the structures that you obtain from that definition, you will see that, well, you get infinite or circular witness terms. So that seems a bit unwieldy to work with. So you would, in order to work with that, you would have to come up with a theory to deal with these circular terms. So that doesn't seem so nice. But fortunately, since all the recursion is introduced with μ's, we actually have regular coinduction, which means that in such a proof tree, you only have finitely differently many subtrees, which means you can turn the whole thing into an inductive definition. And this is also, I think it's more or less standard, so you can find it in this paper by Gaffeyev, Levin, and Pierce, and in a newer one by Danino, so he spent quite a lot of work on that. So there's a standard transformation, which I'm not going into, but you can look at that in the paper, and then essentially you get an inductive definition of equivalence, and you also can construct witness terms that contain explicit recursion. And that's fairly easily. And termination of that process follows really from this fact that you've got regular coinduction. Right, that seems we're good now, right? So now what we can do is we can translate from equi-recursion to iso-recursion. And in order to do that, we somehow have to change this kind of silently unfold anything anywhere. We have to make that a bit more explicit. So in the type system, we put in an explicit conversion rule that, like known from other type system, and that's just there to apply the type equivalence. Yeah, so it's a non-syntax directed rule. You can put it anywhere in your typing derivation, and it's just there to put in your equivalences. Well, to put in your adapters, as you will see. Yeah, so you extend that namely to a translation, and the translation does more or less nothing except for the, well, it's homomorphic except for the places where you did have the conversion rule. For the conversion rule, you invoke the variant of type equivalence that also produces a witness term. Well, and you just interpose it, and you're fine. Yeah, so and it's also fairly easy to show that this translation is typing preservation. That's no witchcraft involved here. Also, you might wonder, can we come back? Well, you can come back also from an iso-recursive system to an equi-recursive system if you assume that the underlying iso-recursive types are contractive. Usually, if you look at treatments of iso-recursion, you don't assume that because there's always, well, the unfolding is explicit, so there's always something going on. But I guess it's for the application that we have in mind, it's good to assume that also iso-recursive types are sort of contractive, because otherwise the whole bandwidth would be spent with unrolling and synchronization, and no information would ever be transmitted. So I think it's a reasonable assumption, and with that, the translation is actually just erasing the unroll statement, and there you go. Now, so the remaining thing, that's also a typing preserving translation, and you're good, apparently. Well, now we learned if I have a suitably nice, a contractive iso-recursive program, can we actually make it talk to an equi-recursive program just by erasing the unrolls, or just by making the unrolls silent? Yeah? So if the unroll doesn't do any communication, you kind of have the same effect. So that was actually the starting point of what we wanted to do. I can say a little bit about the reason. So to do that, we just have to ask that all the iso-recursive types are actually contractive, right? So apparently then we can erase and go ahead. Well, I said that. Well, or can we? So what would this look like? No? I mean, if you want to do that, you would like to prove something, right? So you would like to prove that somehow the iso-recursive version after erasing is still somehow in sync with the original. So okay, let's say we are translating from where to where? From equi-recursive, I think that's the E, to iso-recursive. And then here on the equi-recursive side, we take a step. And then, we take the result, we translate that again. And then hopefully we can also reduce from the original one to the image, to the translation of the image under the reduction. I should have drawn a picture, but I'm sorry I ran out of time. Well, that would be nice if we could build up such a simulation, but no, it doesn't work. And essentially, what goes wrong, I have to go back to almost the first slide to show you what goes wrong. Like this one here. So there's a reduction that introduces this process here. Yeah, so in fact, this process is introduced wherever the translation introduces an adapter. Yeah, so every adapter at the type level looks like this. Yeah, so it actually has to introduce a fork and a new channel, and then, well, of course, the body might look different. Yeah, but essentially, this is what you have to do. Now, if you reduce that term, then the fork will go away. You have a separate process. The process will make some, a couple of steps maybe, and then you're left with a different configuration where you have the original process, the adapter process, and maybe some client processes which are not really affected. Now, if the original system takes a step, well, in the original system, you still have one process, right? Now, if you translate that, you get something with the fork, and you need to relate that to something that already has done the fork, where you have an extra process, and the extra process already did some steps. So clearly, it doesn't work to just assume we can continue from the translated term, because this fork is introduced everywhere. Okay. Right, so that doesn't work. Right, let's try to adapt to this situation. So somehow, since the translation reintroduces the fork, maybe we just went a little bit too far, right? So so there's nothing that I can draw on. So maybe we just went a little bit too far. No? So this was the original term. We made a step, and then so we made the translation. Sorry. Then we made some steps down to here. Okay. Now we make a step up here. We do the translation again. Maybe we can catch up with the term by just, well, here we have this fork stuff, and here we have the term that has the extra process. Maybe we can just get down there from this term. So that's kind of the idea of this situation. Unfortunately, that's also not working. And I would have considered that as some sort of administrative reduction, like in CPS translation. There you actually, if you look at Plotkin's paper, there's a similar situation that the reduction is a little bit ahead of the translation, and you just can catch up using administrative reductions. But here, apparently, it doesn't work like that. So the current thing, maybe you need a simulation up to some equational theory, namely, if your source term makes an alpha step, then your translated term, well, it first does some equational steps, forward and backward. Then it does the actual step that corresponds to the one in the source term. And then you have this equational steps again. So that seems to be the most promising. The only thing is, what usually is understood under equational theory is that you are able to apply the reductions in both ways. So first, I'm not really sure that anyone has looked at session type systems in that way, because it seems that you also have to to do communicating reductions backwards in some places. And the second thing is, as far as we are currently into this problem, it seems you need equations that go beyond the mere reductions. So you need, it seems you need equations that have been shown by Benton and Kennedy and others. So they have been looking at equational theories for Moji's monadic meta language. And they have some commuting equations where you can commute things that have disjoint effects. And if you have that, if you have these kinds of equations, I believe, or we believe, that you can get forward, but that's still up to be determined if these equations are actually applicable in this setting. So, well, so that's the current situation. So initially, I was, as usual, too optimistic, and it looked like it's an obvious thing, and you just do that. Well, from the typing perspective, it is. But here, with proving this kind of correspondence, it seems we are hitting a brick wall, or we are trying to scramble up the brick wall. What would be nice to see after 30 years, that there was some sort of equational theory for session types, for functional session types. If anyone has spotted such a thing in literature, please let me know. I haven't really been able to find that. The other one was, so we discussed a lot also about bisimulation. I think bisimulation would help as far as to the second attempt, where, I mean, with this administrative reductions, where the original term is just a little bit ahead and you just need to catch up. I'm not sure if bisimulation would still help if you have to exercise this equational theory in a more non-trivial way. Well, yeah, that's it essentially. Thank you.
Thank you very much. We have time for questions.
Just about this last slide, you asked whether bisimulation could help. What about coupled simulation? You know that weaker notion of correspondence introduced by Nestman and Pierce.
Okay.
Concur paper which got the test of time award last year, and that's called.
I think coupled similarity was originally introduced by.
Right. No, sorry. No, that's a good point. Sorry. It was introduced by.
Yeah, but I was.
But it was used and.
But yeah, but I was thinking the same, because it's exactly for something that is a little bit ahead of something else.
Mm-hmm, mm-hmm. Yeah, well.
So coupled similarity might be.
Yeah, I'm not familiar with it, but if you have a pointer for me, that would be great if we can find it.
Application in refinement, and it's really if you have something that is in between two bisimilar states, for instance, then you can use coupled similarity to get a meaningful equivalence there.
Yeah, we should talk about it. So.
I think you might also be able to use logical relations.
That's what I tried to set up. If you have any suggestion about that, actually, so I mean, you're doing logical relations. I know that, and there's some. Wasn't it by Jorge Perez even? By Jorge, who is sitting behind you. So there's this paper with Frank and Bernardo, right? And it's so I looked at that, and it seems that worked because you are in this linear logic based settings where each process has a main channel as its objective, sort of, and then I only looked at at Jorge's paper actually. So so far, and there it seemed to work because you could set up the logical relation around that channel, whereas here you can. It's not clear in this functional term what is your focus.
Yeah.
So if
I think it's not yet published, but we're working on a classical setting.
okay, yeah. So if you have a good approach to do that,
But it's,
yeah, that would be helpful.
And
So
I
so.
think what you can do with a logical relation, you can do this coupling because you can relate, like,
Mhm.
you can relate different configurations.
Yeah.
Yeah.
Yeah, so that was actually one of my first thoughts. Then I looked at their paper and I realized, okay, it works, or this approach works because you have this single channel that you can narrow down on, and you only have to, well, only, you can use the type of that channel to guide everything.
Right.
Yeah, so if you have a way of generalizing that, then
Well, you're
help us.
You're hiring my co-author as a postdoc, so.
Okay, good, yeah, well. He wanted to do some other topic, but anyway, so he won't.
Thanks for the talk, Peter. So actually, there are many interesting things. So my first observation when you were presenting this was like these definitions of type isomorphism, in which you have, well, you want to acquire two types, and then you find witnesses for two types, and then you make sure that the two types, witnesses are essentially equivalent to the unit or something like that. We did that also in conjunction with this logical relation. The logical relation was giving us the equational theory for that approach. So that's that could be one way to go. But also the idea of the logical relation, actually, it's you can overcome this one focus point, right? So there is this formulation of logical relation based on classical linear logic, also by Luis's student Pedro Rocha. So he had this way of proving like the usual stuff about like termination, confluence, so on, using logical relations in that context, and that was classical linear logic actually. So there is a different range of possibilities. I would say.
Okay, so there's slide.
Yeah. Yes.
So, thank you again.
Thank you.
Yes, thank you, and thanks for letting me talk at this event. Yes, I will talk about a little bit about mechanizing in a proof assistant session types. I won't say much about how to do it. I think you should follow the next talk for that. But I will talk a little bit about projection. So this is a joint work with my PhD student, David, who's been doing all the technical things, of course, and Jesper, who is an expert in COC, proof assistant. And yeah, this is based on an already published paper. And the whole idea started with this project called Mechanist. And the main goal of this project is not completed, to basically mechanize the theories of multi-partition types in COC. And particularly, the idea was to start from this paper, so the original paper and then the journal version of the multi-partition types. Okay, so focus exactly on that theory, and why we want to do that is, well, you should see next talk, why you should do these kind of things, but there was, for instance, realized before starting the project that in that paper there was like a missing rule in the semantics of local types. And actually, while we've been running the project, we also realized that there are lots of things that, lots of imprecise things that, and I think that this paper is one of the most detailed papers when it comes to proofs about multi-partition types, I think. And already there, despite there's lots of details, I think there's lots of small things that you overlook just because you pen and paper. The idea is to formalize the whole thing. Now we are actually working on this part here, which is basically formalizing the type system and proving subject reduction and session fidelity. But what I'm going to talk about today is about projection. and something that, nothing wrong there, but something that came out from the mechanization of the projection of global types came out just by doing the mechanization. We realized that we needed something. Something was not in place. Nothing wrong, but we wanted to extend, let's say, the way the projection works. So let me talk a little bit. I assume everyone knows about what global types and projections are here, but basically a global type is, the idea is that you go from binary session types where you have only two ends in a session. This is what Peter was also talking about before. And what you want to make sure, what you can use session types for, you specify how a particular channel in a session is going to be used, right? Then you use duality, being careful with recursion, of course. And then you can get a specification for how the other end has to behave. And when you move to, if you want to do multi-parties or more than two parties, then that's not sufficient, just using duality. So you need something built on top of that. So you have this kind of specification language like global types based on the idea of choreography, where you can say what kind of steps the session has to take during execution. By the way, here I have, like in the original paper, I have these explicit channels. Nowadays are not used a lot anymore, but we have them in this mechanization. And basically what happens when you do projection is that you have a specification of how the sessions should behave given as a global type, and then what you want to do is you generate some local types which specify how each role in the session has to behave, right? And the way projection works is you can also, the idea is to look at, for instance, if you want to project Carl, then you look at how Carl in the global types behaves. And the way you can also look at it is by erasing it. So you erase all the behavior of the other roles, and then you get that, for instance, Carl first has to make a choice and communicate it to someone else over K, and here is the projection, and then on one branch it will send a string on K prime, and the other branch it will send an int. Now the point is that when you have branching, and you look at Alice, Alice is not participating to the, to this branch here, right? So in some sense, Alice has to be notified, or if it has to behave differently on every branch. And what happens, at least in the original paper, is that there was a kind of easy restriction that said, well, when you do projection, if you want this projection to be defined, it must be the case that anyone who is not participating in the branching, like Alice here, behaves the same on both branches. So in this case, for instance, it's fine, because if you look at the projection of Alice, it's sending an integer over K double prime. This is fine. There are generalizations of this. This is not the most general way of doing this. In general, the principle is that if somebody is not participating in a big difference. Now the problem is that if you add recursion, then things can get weird. Okay, so let's look at this global type here. Then you have two recursion points, one on recursion variable t, the other one on recursion variable t prime. And you can see that the specification here says that Alice must send a string to Bob. Then there is another recursion point. Then Carl must make a selection with Dave, either go left and right. And then the funny thing here is that if it takes left, then you will bounce back here to the beginning. However, if you take right, Alice must send a string to Bob, and then you recur again, but up here. Okay? So it's a very strange global type somehow. No? And you also may ask, why would you ever write something like this? But so first of all, if we look at the restriction I talked about before, here Alice is not projectable. Okay, so this global type would not be projectable because Alice is sending an output and then recurring to point t prime. Instead here, it's just a recursion to point t. So this would not be projectable. However, let's look at this global type here. It's there's only one recursion variable, and basically what happens is Alice is sending a string to Bob, then car makes a selection, left or right with Dave, and then you go back to the beginning. Okay? And this is projectable for Alice because the behavior of Alice is just go back to the recursion point. Okay? Because the projection is a very syntactical thing, so you need to look at the syntax. And now the question is, well, if you look at Alice, the way it behaves here, it just continuously outputs a string. But if you look at this, the way it was designed, actually Alice is doing exactly the same thing. And if you indefinitely unfold, so you look at the fully unfolded infinite trees, actually this guy and this guy are the same thing. So basically, this is an example where ordinary global type projection fails for basically the same thing, the same global type. In one case, but it doesn't fail at the other. So the main issue is that it's understanding how to deal both with recursion and branching. This is usually the standard way of defining this from the original paper. There are different versions of this. But the whole point is that you fail in one of the cases because you have this check that all branches must have the same projection if they are not part of the branching. There are more recent, at least at the time of writing the paper. I think now there are other versions as well. But this was the most advanced one. But still it was failing the example I gave you. Now, if you look back actually in the 2008/16 paper, there is a hint about, and I think Peter, you were also mentioning this in your talk, about looking at a regular tree representation of these types. And basically what the whole idea is to actually give a coinductive representation of these global types. So basically you have the finally the fully unfolded tree. And actually this idea was originally, if I'm not wrong, given in this paper by Gilles-Zal et al. And the whole point was to have a definition of, a coinductive definition of global types, and on top of that, give a coinductive definition of projection. Now, if you do a coinductive definition of projection on coinductive global types, you don't have any more that problem. So those two types that I showed you, they are the same thing. So you will be projecting on an infinite tree. However, and this is fine, and the way I would like to look at this as their projection, right? The projection is correct. However, you still want to work with something like this. You want to have a finite representation, and you would like to work with infinite types. With inductive types. And the question is there a connection between these two things? Now, and again, the point is that these two guys here would be the same object. Now, this direction is already been done by David, Francisco, Lorenzo, and Nabucco. They have this paper where actually they mechanize in Coq all this setting here, and they take the standard projection that I've shown you, and they show that if you take an inductive global type with an inductive projection, they show that what you get here is something that makes sense also in this world here. However, the opposite direction does not work because of the example I showed you, for example. Because this projection that you have here is not complete, basically. And basically what we did in this paper, while David was trying to mechanize it, he realized this and he tried to prove it, and then he succeeded, was to actually find a new definition of projection that is complete, and then proving that actually it corresponds to what you have here, to the coinductive world. Now, what was the problem again? If you remember, the problem was that you had to check branching, and when you have branching, and here I've just simplified. I turn Alice into A, Bob in B to B, and is Carl, I think this is Dave, just for compactness. But the whole point is that you want to check when you always have the side condition that when you project branching and you're projecting a row that is not branching, you want to check that they are the same. And in this case, it was working, while if we look at the other case, it's not working, simply because this type here, whatever that is not the same as this one here. Well, the projection. And the point is that you're missing context. So if you look at this, basically the way projection works is local, in the sense that I'm projecting this particular subterm here, and I only want to check that the projection of these two guys is the same. However, I forget that this T is pointing back to the context, to something that I've already projected. And here, the trick of just unfolding doesn't work, because you will recursively end up into something like this anyway. So how can you do that? So a possible solution, which works, but it's kind of annoying, is that you define a context, right? So basically the context is what you have projected until you get to the projection of the branching, right? So when you get to this point, basically what you want to check is that the context applied to the projection of A here is somehow equivalent to the context applied to the projection of A on the other branch. And basically, if you do this, what it boils down to is to checking this recursive type equivalence, and we've seen that, we know how to do it. So that's a possibility. Yeah, this is, we have seen this also in the previous talk, so I won't go much into this. However, the annoying thing is if you do that, somehow you need to carry your, behind the context of this projection. So the way that we do it instead is slightly different. So basically what we do is to first run the projection normally. I will tell you in a minute. So compute actually a candidate projection for one particular row, and then, so you get some local type T for projecting the A, for example, that I showed you before, and then what you need to do is to run some sort of validation process to check that that T is actually good enough. I'll tell you in a minute what I mean. But what you see here is basically some sort of coinductive relation. Actually, here I'm going to cheat a little bit because I'm telling you how to compute this as well. But in the paper, we have a coinductive definition relation defined on inductive types. And then on the side, we also provide an algorithm, which is kind of standard for computing that relation. Just an example, just how, I show you how we do it. So basically when you get to, this is basically for computing the candidate output, so the candidate projection. And basically what you do is here, if you remember the standard way of projecting, here there was also an extra condition that checks that all branches have the same projection. Well, here we say, well, forget about that. We want a total function. Project anyway, but just project the first branch, okay? So we just do that. And now you say, okay, but that's weird. Why are you doing that? I mean, how about the other branches? What if something goes on differently? So this is how you do it. It's very standard. However, then we have a second step where actually we need to check that what we have generated from this operation here is somehow compliant, is projectable. So it's compliant, is related, or equivalent, whatever you want to call it, with the global type that we originally had. And that's the way basically to remember what the context is. And the way it works is that, so for instance, if we project A and we get an output of an integer here, we got this term here, and this was the original global type. So you start doing the projection. First you look at A, okay, this one matches, so you just do a matching, like by simulation really. And after you do that, you will get basically this G2 here. and you need to show that it's equivalent to this term here. It's related to this term. You need to unfold once, and then you will end up with this thing. And here where we had the problem, where we had to check that the projection of G1 of A in G1 is the same as the projection of A in this thing here. So what do you do here?
How many times do you have to unfold? When is enough?
You unfold I think you unfold every time you meet once, you unfold it. And you do it once. And I think that if I remember correctly, it can happen only twice in the algorithm.
Twice, right?
Twice, yeah.
Then you can not commute more.
Yeah,
right?
so the point is that the algorithm works like it's a standard coinductive for regular coinductive trees. Once you meet you have some storage, you save if you meet something that you met before, then you're done. So it's not very complicated. It's not very complicated. But you need to unfold. I mean, the rules are, so the relation, now that you've asked, the relation is this one. And this is coinductive, and we have some unfolding points that you need to do. But I'm not going to go into details here, but yeah. Right. So, but then when you get to this point, it's here that you check that all branches are compliant. They're kind of equivalent, according to this relation, to what you got here. So basically you get two subtasks. You need to check that G1 is equivalent, is related, for role A with G1, and at the same time also this one. And now you can forget about all this recursion thing, because it becomes, it's part of the relation itself. Yeah. And it's really, what you do here corresponds, it's not the same thing, but intuition is what you have back here, where you did basically a pure syntactic check. All right, so I think I don't have much left. So basically the way our projection works is that you compute this candidate projection, and if it's related to G that you're projecting, then that's the result that you have. Otherwise, it's undefined. And basically what we prove, and this has been mechanized in Coq, is that so we have a relation called unraveling that actually I think comes from the Zoid paper, the one I was mentioning before. But basically it relates this world with this world. And the point, what the theorem basically says is that if you have some G, you have some G here, then there is some G corresponding to that here, the coinductive version of it, and you do the projection here, then that's corresponding to the projection you can also do. So it's basically equivalent. Yeah, here it's basically, if G is coinductively projected, then all inductive representation of G are inductive projection. So basically you have a sort of equivalence class, if you want, over these new terms that you have. Yeah, so here is some facts. Yeah, basically, well, you always can check if something is projectable by doing this check here. Yeah, here maybe to Vasquez, I always unfold some of the mu t's. Termination has actually been proven by, and it's basically by well-founded recursion. And this one, I haven't checked this, but this one I had it from David, the complexity of the projection. Some related work. So there are many other mechanizations of projection. I think also not only for multi-part decision types, but also for choreographic languages as well. But really what our mechanization at least, and also what came out of this it comes from this paper here, from David and the others. There is we didn't know about this, but there is a talk later by Felix. I've never met Felix. Hi Felix, nice to meet you. I've heard this from David. So, but there is this paper here where they actually have some similar results. I think you're, I don't know, but I haven't had the time to check it, so I'm looking forward to listening to your talk. But you work with automata there, and but I think, as far as I understood, you have a more general also language, so and also more general projection that doesn't enforce that you behave basically the same up to recursion on every branch, but you can do other things. Yes, and I think yeah, that's it. That's the conclusion. Yeah, but if you want to know a bit more about COP, it's about 5,000 lines of code, and yeah, the mechanization is public available. It's linked from the paper. And now basically what we're doing is we're trying to prove the subject reduction with these types. And then the special thing is that in the original paper there is this notion of linearity of global types, because you don't have a channel for every ordered pair of rows, but you have just, it's like a shared memory if you want. You have just a limited set of channels, and for that you need to make sure that the global types doesn't do weird stuff, doesn't generate races basically. So there is an extra check that you need to do on top of that. And we have mechanized that and also shown that it's decidable, but it's a little bit more complex than to show that how subject reduction and session fidelity work. Thank you.
Thank you very much. We have time for questions, I think.
Also, I'm asking merging. Your method probably we can easily extend merging, right?
So merging is basically the operation that allows you that allows different behaviors, right, on every branch. So my guess is, so the problem that I showed you is there even if you have merging. That one is really easy to show. Maybe not exactly with that example, but I don't think it's very difficult to come up. I think we have an example that shows that merging fails as well. Whether it's easy to mechanize and do that, I don't know, because we haven't tried. So I don't want to say yes, I think it's possible to do it, but
theory probably you can.
yeah, probably the theory is, but I mean, but the idea is also to have the same result, you need to first find the projection. And using the same technique, I believe it works, but then you need to factor in this merging thing, and I don't know what happens there. We haven't thought about it.
Hey, thanks for your talk. I only had a little time to look into your paper, so I wondered, you motivated with this example that Alice doesn't know about the value choice by C and D, and then you converted it into another type where, because it actually wouldn't need to know about this earlier branching. So do I understand correctly that still with the, because you only project onto the first branch, you cannot support protocols where somebody else than the ones in the choice would learn later about the branch?
Sure. So the main assumption is that we focus on this projection here. Yeah. And this projection says, okay, we know that you can make it more interesting and more useful, but here the point was, okay, what's the easiest way to actually have something reasonable where we can rise unaccepted? Okay. And so then we focus on this, then the check that we do to deal with this recursion adopts this assumption. So as Nabucco said, if you want to do merging that allows different behaviors, so I mean the whole principle I believe is, please somebody tells me what you chose at some point. If so, maybe it depends. Okay. But there are different generalization of this, right? So in that case, I don't know how to do it.
Yeah, I was just continuing on the same line. It seems to me that here, by picking G1, we just already implicitly assume that all the projections on all the GIs are the same. And therefore, I don't see very well how this could be generalized to the case of merging.
If you do merging, probably you will need to change this translation. My guess, okay, can I give you a guess? So my guess is that instead of picking G1 here, you will take the merge, and then you have an issue, because then you need to make sure that merge is compatible with recursion. And but since it's with local types, maybe it's not so difficult. I don't know. But for sure, picking G1 already here, as you said, Ilaria, implies that you will just check later that they are equivalent to G1. Absolutely.
One last question.
So can I share my guess about the merging issue? So because my interpretation of your talk, which by the way I think was very nice, is that you're trying to give a semantic, you're trying to look at this particular condition that was strictly syntactic in the original definition from a semantic point of view. And I would have expected that merging would have been like, okay, you would have leveraged on that semantic approaches to also accommodate merging. But of course you know more and you're more skeptical about how things could get.
I think I'm sure Felix in his work they do it. So
We don't do merging.
you don't do merging, okay.
No.
But it's future work. So.
Okay, you don't do merging, but you realize more flexible.
We don't need it. That's kind of the point. Yeah.
Okay, let's thank the speaker
Thank
again.
you.
And we come to the last talk of this session, which is given by Lorenzo, and it is about the concurrent calculi formalization benchmarks.
Okay. Eccolo, there we are. This should work. Why? You can see, right? Okay. Good morning, I'm Lorenzo, and as you can see, I'm one of many. And I have the honor and the pleasure to present to you the concurrent calculi formalization benchmark. We start from a very simple aim, simple. We want everyone to mechanize session types. So first we wanted to mechanize session types ourselves, and multi-party session types. Then we think this has value, and we want the whole community to engage in this. Let's say we want more and more paper to be accompanied by mechanized proofs. And when I say mechanized, I mean, you saw an example, just in an example, right? Marco presented something that was mechanized in Coq. So I'm talking about this kind of softwares, proof assistants, like Coq, Isabel, Agda, Abella. There's many, and this was not a complete list. Anyway, so we focus on this work. We wanted to do mechanized session types using these kind of softwares. And we kind of, this is the main motivation, right? We like them. We kind of did also. Many of the, actually all the authors, all the participants in this process, this project did mechanize something. And we think that this thing is, the mechanization for a research paper is fun and useful. First of all, when you mechanize computer science method theory, programming language method theory, you can get out of the mechanized proofs and definitions certified code into a target programming language, mainstream programming language, because you could consider the proof assistant a programming language itself. Then also mechanized proofs help you avoid mistakes in overlooked cases. Marco had some examples of make life easier. Papers can miss a rule, or they don't show the proof in so much detail, and some case of induction is just by induction hypothesis, and then it's not. So a proof assistant will not, in your interaction with it, will not accept it. And to be fair, this is it's been my slogan for a while. I'm not saying that proof assistants are better than pen on paper proofs. They are more. So it's not better knowledge that we seek more knowledge. We seek to understand more about our theories, our developments and research. Okay, so we are excited about this. We have our experience in mechanizing session types, but it's tough. It's hard work. And therefore, we decided to take a step back. To take a step back and to start talking to each other and to the community as a whole in the spirit of the POPL-MAC Challenge. Probably you know about the POPL-MAC Challenge. It's a very influential community project and paper from the early 2000s, where, again, many very, very smart people, very, very good researchers came together in the community of programming languages and had this document presenting some mechanization challenge, some benchmarks, detailed, to the programming languages community. So they highlighted these challenges were based on a system that highlighted some fundamental features of programming languages. And they wanted to do what we want to do, but in a different context. So these projects, these benchmarks, want to encourage discussion in the community. They want a discussion, comparison of different approaches and of different programming language. Yes, maybe, but also of different proof assistants. And through the development of guidelines, tutorials, more support, more often than not, proof assistants don't offer the user enough support. And all of this for reusability. And in our case, all these things in our benchmark will focus on session types and concurrency. As I said, we took a step back from all the hard work of mechanizing our theory of multi-party session types. We took a step back and we tried and identify as challenges, as fundamental challenges, some topics that we would encounter over and over again in our mechanization and when developing our theories for our papers. And these topics are from the literature. They will not look new to you, hopefully. And we have identified these three ones in particular, and we have developed our challenges according to this division, these three topics. One is linearity and behavioral type systems, so the actual session types or behavioral types. Then we have two challenges that only deal with processes, so we rule out the types for now because we wanted simple challenges. We wanted to isolate the problems. Second one is deals with name passing and scope extrusion. Also, this should be well known. And finally, coinduction and infinite processes. Again, my work is very easy now because both talks before mine mentioned coinduction. That's our small website. It's work in progress, but please have a look. You can find the technical report with the details of the challenges and also how to join and start discussing these things with us in case you're interested, and I hope so. So let's start. I'll just present the challenges, right? The first challenge concerns linearity and behavioral type systems. So we give, first of all, a simple language, a simple plus-search language with values. Now, A is a value, L is a variable for values. Then we have a terminated process, the zero, and a send construct and a receive construct you can see that the send construct sends a value, while the receive needs to receive via x, so via an endpoint x, over a variable L. And that variable is bound. Very, very interesting for mechanizations. Not really, but tedious. Then we have, parallel composition, as usual in concurrency. And finally, restrictions of 2 endpoints. So here we use 2 names for the send and the receive. We restrict the 2 endpoints, the send and the receive endpoints of a channel. Okay, these are processors. Again, nothing should be surprising, and not even in the semantics. As you can see, the main rule is the first one there that explains how a message can be sent and received, how communications happen. And under a restriction, so after we declare the 2 endpoints, x and y, a process can send via x a, the first one, the one on the left, to the one on the right, will receive over y on the variable L. And then the step can be performed. Again, as you can see, after the reduction is performed, the step is performed, the process there, for the right-hand side, the process who receives, continues as Q, the syntactic continuation, with a substitution. Again, so much fun mechanizing substitution. So then we have other 3 rules in our semantics, which are just to make sure that the semantics is compatible with the language. But the last one, which factors in structural congruence, I will not go into detail, is a pretty standard. Any, I don't know, process calculus paper will offer some. It's in our technical report. So you'll find it there, but no surprises. Now we want to type. We want to type with the processes to achieve these 2 things. And we give to the aim a type system. And we have our session types, let's say, which are very simple. End for the terminated process, base for our values, and then a send and a receive type. Actually, a receive and a send type, and that's it. We have context for value variables and for endpoints. And that's our typing system, our type system, our typing rules. Again, very much standard. The important thing is that, in particular, the second rule, TPAR, is the one that allows us, that enforces the first point. So no endpoint is used simultaneously by parallel processes. This is enforced by the splitting of context with the rule to TPAR. The second thing is the 2 endpoints of the same type of session have dual types. Again, duality, here I mention it. I don't introduce formally, pretty standard. Please look at the technical report on the website. However, 2 endpoints of the same session have dual types, namely one sends and the other receive. And this is enforced by the restriction typing rule, okay? So nothing surprising. And here comes the challenge. So we asked the mechanizer to display their techniques and their proof assistants when proving subject reduction. We should be familiar with this. Typing is preserved by reduction. And second part of the challenge, well, you can also prove type safety. For type safety here, a well-typed process is well-formed. We'd have to introduce a well-formed predicate, details in the technical report. But basically, what we are enforcing here is that no 2 endpoints are both a send construct or a receive construct. So again, it's a duality, this time defined not on the types, but directly on the processes as well-formedness.
Are you sure this is the subject reduction you want to prove?
I am sure.
Okay.
I am sure.
I don't think it works. But
it does. There is, if I don't remember,
right?
sorry?
The delta should change.
No, they don't. There are 2 approaches. I was surprised at first as well, because I'm not, now I am, but I wasn't when I started the session type person. But you can have the subject reduction with the types staying the same. People here can explain better than I do. It's in the technical report. And there's also a note about this question. Now, I don't remember myself.
Or maybe it's because the way you set up the reduction proof.
Yeah, it's the typing and the reduction, yes. So you'll always be able, I think, if I can try and give the intuition, but I might be wrong, so my co-authors, please, correct me.
Yeah, don't waste your time on it.
No, it's just, I think it is because the type of, sorry, yeah, typing okay, but it's because the send and the receives happen under a bound.
Otherwise, balance.
Yeah, so it's under the.
No, no, but also the original paper, it's the same, because when you have
Thank
two dual sides, they cancel them out and they become like a bottom in
Yeah.
the original binary session types. So you have the same result.
Yeah.
So they're gone.
I have the same question about the second year.
The what? Sorry?
Yeah, also the same result.
I couldn't hear. This is supposed to be. It's good, it's good. So this was supposed to be basic, right? Like traditional session types. You should have known. Sorry, you were asking something.
I have the same question about the second year. Don't you want a stronger result there than the fact that
About that, you can, of course, have stronger results. This is on purpose simple. So this, nothing new in these challenges. This is identifying some fundamental and well-known aspects of the theory of session types and concurrency to be mechanized. Then, hopefully, many people can mechanize them. This is supposed to be something that people can do, but in the process, they will display the feature of their proof of system, their great idea of techniques of how to formalize. They will develop a tutorial. So, yes, probably you want something stronger if you really have to develop your own system that works. But here is just isolating the bare minimum. And you'll see also in the next two challenges. Let me go quickly through them. So the next one is about name passing as scope extrusion. So processes. We give a slightly different calculus, again, with this idea of isolating things, of isolating the feature that we want to mechanize. And here is the same constructs, but if you can see a send and receive, well, restriction sends only one name, but it's a choice, not really a difference. The real difference here is that we send and receive names. And actually, we don't have values, because we wanted to isolate this simple behavior. It doesn't have to be meaningful. It has to correctly capture and isolate the behavior for formalization, with the purpose of being able to mechanize it. Here I show you this challenge through a relevant example. So this is a process where so this is a process that has two processes in parallel. The one on the left introduces via restriction a variable y and sends it. It wants to be able to send to the process on the right that will receive it on x on the variable z, but at the beginning, when the process looks like this, the scope of the new binding is only the left-hand side. So this scope needs to be extended. Again, standard concepts. From the literature, we found two approaches. We can represent formally this idea of extending the scope. And one is through a combination of structural congruence and the semantics defined as reduction. So first, sorry for the mismatch, so we have to check in our example that the y is, the bound variable y is not in the free names on the process on the right, so it's a bit of substitution of renaming needs to happen there with respect to the rule. But anyway, once we check that that variable is not on the free names on the right and of the process on the right, we can say that these two processes are structurally congruent, and then we can perform a reduction step simply with a rule. I will not present all the semantics really, I was just mentioning that there is a rule for communication from send and receive, and a rule for that lets the reduction happen under restriction. Okay, this is fairly simple. Then there's the alternative approach, which is instead of structural congruence and reduction, we use a label transition system to define the semantic. We want to prove this, then, which is the same, we have the same process and the same resulting process on the right, so the same starting process and the same resulting process, but instead of having one step of structural congruence and one semantic step, we have one single transition, label transition, with a silent transition tau. And there's how we prove this. We start from, we go bottom-up reasoning. So we prove the red thing, and we have a rule for that, which is a closed rule that allow us to capture both branches of the parallel under the restriction, even this pretty standard. But then to have this, we have to prove the two things in red, which is an output and an input. In particular, we see that the output on the left-hand side, it's a bound output, so we have to open it. Again, here, to make things sound, we have to distinguish the actions between free send action, the one on the top, and a bound send action on bottom. It doesn't, I'm not going into detail here, it's in the technical report. Again, the important thing is, when mechanizing, we have to take care formally of these things, very carefully, otherwise the proof assistant will not accept. So to make things sound, we chose this approach. And then finally, we just finish our proof with a simple output and a simple input rule. Last, okay, first the challenge. So I presented you the two approaches. The challenges says, okay, please, ask the mechanizer, please prove that the two approaches to model scope extrusion and impulsing are equivalent. These are the theorems. I'll go quickly to the next one. Anyway, also these things, they are all from the literature. They shouldn't be new. They are sometimes new to me because I didn't study all of it, but they're not anymore. Then, co-induction and infinite processes. This is the last challenge, sorry. This is the last challenge, and it deals with co-induction. Very similar syntax as before, values, variable. The only thing is the only new thing is the thing in green, which is replication, which actually introduces infinite behavior in our processes with this rule. Now, the semantics, again, I will not give it all. Check the technical report. Is given as a label transition system. And this is the rule that introduces infinite behavior. As you can see, the process P, if the process P step, the process exclamation mark P is allowed to step to a process that adds in parallel, replicates itself with a parallel construct. And this step can be clearly done an infinite amount of time. So how do we deal with infinite behavior? With co-induction. And in particular, we start saying, how can we relate to process with infinite behavior? How can we reason about the behavior of processes? Well, by what we can observe externally. And what we can observe externally in a communication setting is only what's sent and what's received. So we introduce a predicate formally that tells us if a process can perform a send or a receive action, as usual. And this is all we can observe. This, again, very, very standard. Then we define a strong bar bisimilarity. And here is co-induction. You see the word largest, the larger symmetric relations such that, and we have to condition P, whenever P is related to Q, we have that what's observable for P is observable for Q. And then if one of the processes steps, then also the other steps to something equivalent. Okay, these are equivalence, strong bar dissimilarity, but not a congruence with respect to context. Here you have a small example. So what do? For this challenge, we introduce strong bar congruence. So we define this congruence that way. So basically we enforce we say that two things are related if, by congruence, if they are bisimilar for when substituted in every context. And of course, once we define, we have to prove that there's an equivalence relation and a congruence, and it's included in strong bar bisimilarity, very standard. And finally, we have the main result, and that we ask the mechanizer to prove as a challenge, which is the theorem that characterizes strong Barbet congruence via substitution and parallel composition. I'm done with the challenges. So we ask the mechanizer to take these challenges and to complete them by mechanizing the definitions and the proof of the theorems of the result I have presented to you. I have a question for you. Was this tedious? Because the answer is kind of positive. It is. In particular, it's tedious when you have to repeat the mechanization effort for each one of these concepts every time you want to mechanize a new system. You have your own novelty. You have your own new idea on a system of session types. You love it. You want a mechanized proof. You know you can do it. And then you start, oh, okay, I have to prove subject reduction, or I have to take care of scope extrusion. So for this reason, for the tediousness of that is intrinsic in a mechanization effort, sometimes it's fun, sometimes it's tedious, we want a community effort. We are asking for a community effort that will develop, ideally, and we will be very happy in case, we'll develop tutorial formalization for different approaches and different proof of system. Comparing the proof of system. So, you know, Coq can do dependent types. Isabel has classical reasoning, these kind of things. We want to have this comparison, maybe in a better way, a more friendly way than the usual, but focused on session types and concurrency. Hopefully, this will establish best practices so that you know that if your system that you want to mechanize has needs coinduction, you know where to go for, what proof of system to pick, and right, perfect, I'm closing, and how to do that. The first 3 points are the benefit for us, for the community of session types. The last 2 are the benefit for proof of system community. They can investigate the strengths and weaknesses of their proof of system and improving on those. Why contribute and how to get involved? Now, if you are interested in this, talk to us. We have a mailing list, that one. We have a website for you to check the technical report, engage, try and mechanize something, play with that. And again, the why is what I tried and highlighted throughout the talk, is the relevance and interest for our community, our problems, and other people's, the proof of system community, connecting this to the community, conducting your own mechanization. That should be, at least for me, it's fun when I manage to do it. But also it leads to publication, both of the novel system that you really like, your novel system, what I called before your novel system, and also you can publish both experience reports and tutorials, and this again will benefit the community. Also, it has a pedagogical value because you can always start with your PhD student or with your colleague that wants to get into proof of system with one of these challenges, which is self-contained, pretty small, a good starting point. To conclude, this was, for the purpose of my challenge, the quote, how close are we to a world where every paper on programming language is accompanied by an electronic appendix with machine-checked proofs. Blah, blah. We only have substituted that. Very simple. Very, very simple. I'm done. Thank you.
Thank you very much. We have time. Yes.
Yes.
I think I have a very high level, maybe a bit nasty question, which is, if you take like now one submission that you prepare and without mechanization, and you then want to submit with a mechanization, what do you think is the overall like head of work, and how would that slow down the pace of publications and submissions?
It depends. Are your co-authors good mechanizers? Because in case,
like the very first paper I authored was actually pretty much this for a different domain, and it takes quite some time for people to pick this up. But then, in the meantime, you have like 2 sub-communities, one using mechanization
I think,
market, right?
so,
That's
yeah.
kind of one of, like, what do you think, like, what's the overhead? That was the actual
The
question, right?
overhead, in my experience, can be months, can be almost nothing. It's true. It's true. Depends on really on how you engage in that, right? It depends. If you add, I don't know. We are doing economics now, but if you add one coder who's a good mechanizer, while you work on the theory, they can mechanize or this thing. I don't know. It usually has some overhead. That's exactly however the point of this, right? Because if you establish best practices, why am I? Yeah, I wanted this, where you can see the website. Sorry. When you establish best practices, that would be the aim. Of course, it's not simple, but that's what we do, no? We do new things. We do research. We engage in things. We try.
There was the question over there. Yeah, you.
Okay, so thank you for the talk. Most of the times we need to combine features, right?
Yep.
For instance, working with a level transition systems in a linear pi calculus. So what you're proposing works very well because you're working in isolation, but the combination has impact.
Of course.
It's not just summing, right?
Of course.
So what I suggest is that what would be the simplest combination that makes an interesting challenge?
So the challenge was thought, the challenges were thought exactly to isolate these things because we are aware of that. We hope that as when the solutions come and we plan to publish them on the website, maybe someone engages in this kind of combination. And we will again go through the whole process of finding support, some tutorials, some best practice. This is the whole idea of the process. We started very little because we know that already this requires some effort. Of course, when you combine two, it's not the sum. But that's why we started the process, the project, sorry. Then, of course, you might want more things. There's nothing about multi-party, for example. So the whole projection, and Marco presented, the merge problems, the conduction there, sorry, it's not here yet, but we had to start it somewhere. Sorry.
Okay, very, very fast. Marco.
I just had a comment, maybe with respect to what Felix said. I mean, after the first popular, hasn't the number of mechanized papers
Yes.
increased over the years?
Yes, it does. At least that's the claim in many places. Yeah. That's the claim, at least. I haven't seen the number now, but that's the claim and what they report. So it's dragging attention on this.
Simon suggested I bring it up in the panel so we can discuss
Yeah.
later.
And last question.
Yeah, so I have a philosophical question. So if you look at the three challenges, then 2 or 3 are classic process calculi issues, right?
Oh,
So,
hopefully.
and then the challenge I understood was about session type. So if you think about session type being more going beyond process calculi, going beyond the pi calculus. So what is your view actually to engage into people to beyond process calculus? Because at some point I think that one of the impacts of sources of impact of session types is that it can go beyond the pi calculus, right? So you don't need to learn pi in order just to do session types.
Okay, can I answer?
That's
Do we have
one
time?
point. The other-
Fast.
In my impression, I thought that all these things about the pi calculus and equivalence of the pi calculus had been already addressed in Isabel by Joachim Parro and students, but that was my impression. Or like, I thought that they had already solved them.
Yeah. This is not new work. First of all, this is not new work. We wanted to start it from something, and we wanted a unifying container, not even to have all the same formalization to be normative, but to contain everything. And we wanted to start from session types, but since it was very hard, we tried to isolate some features that you will encounter no matter the system. I understand that if you only do session types, you might not want to calculate, so you might not even care about the relation, but usually types are for typing.
If you have some concurrent lambda calculus, you don't need to care about name passing or extrusion in the explicit sense that you're doing it here. That's my
We started somewhere. That's my short answer. Sorry, Kristen. But we can discuss more later, of course.
Exactly. Let's thank the speaker again, and we have coffee.
Thank you.
introduce you properly. And Vashka will be the chair for this session.
Okay.
But because we didn't start with a welcome this morning, I'm just going to do a little
Okay.
welcome.
I will get
So welcome back, everyone. And because in the first session this morning we just started straight in with the talks in order to keep to time, so we didn't start with a welcome to the workshop, and then this session the timing is a bit more relaxed. So I'll start with a welcome to the workshop. So welcome to the Session Types 30 workshop. Thank you all for coming, both speakers and audience. To have a good celebration of 30 years of our field of session types. I'll just briefly thank Diana Costa as co-chair, who has done a lot with the general co-chairing and also some of the local aspects of co-chairing. And thank you also to the programme committee members and the organising committee members, as well as everyone, as I say, who has come to present talks and also to listen. So we have this session is the invited talk and keynote talk by Nobuko Yoshida. I'm going to hand over to Vashka Vasconcelos to both introduce Nobuko and then to chair the session. So Vashka, would you like to come up and introduce Nobuko? Thanks.
I don't need to be introduced.
No,
so I can straight forwardly. This is This is originator session type. You are here soon.
So not I just took away my first sentence is that I'm sure she doesn't need any introduction, but still I was asked to say something. Well, in fact I want, but I want to. So I met Nobuko-san more than 5 years ago, and it's true. Yeah.
5 years. Yeah.
You don't need the SMT solver to check the validity of the session. So, but anyway, so we were students and we were working in exciting things like first CCS and then there were other students also there, and some of whom you may know well, either because you met them personally or because you read the papers. And I'm talking about Honda, Kawai-san, the reason why we are all here, and others like Kubo, Makoto-kun, and Takeuchi, Gaku-kun. So there's some of the names that were studied under the supervision of Tokoro-sensei. So the next time I met Nobuko-san, she was in Europe, in the UK, living in Brighton, and at the Cox, the School of Cognitive Sciences at the University of Sussex. Then later on, met her at Leicester University, and for quite a few years, she was at the Imperial College London. And recently, she got this prestigious chair at the Christopher Strachey at the Computing Science at Oxford. So Nobuko-san, she has published hundreds of papers and has thousands of citations and tons of H indexes. But she has been doing
in the beginning, not in the beginning, she has been looking into process calculi, first at semantics of programming languages, and then one of the, I would say, a key point in a scientific course was the multi-participation types in 2008 at Popple, which was become most influential paper, and you've seen here also in Marco's talk a citation of the journal version of that paper. So in the last few years, you've seen that she has been working mostly on multi-participation types, and one thing that I really appreciate is that she's looking into mainstream programming languages, and it's not just toy languages like the PyCalculus or the RandaCalculus, and trying to bring all these ideas about verifying protocols and into mainstream languages. So because life is not binary session types only, and she's a good witness to that, she was talking what is behind the binary session types. All right, thank you.
Thank you very much. Very, very much. This is one of, in past, we wrote slide by handwritten, and this is written by Kohei, and this is the types of processes, and some process, their process are living, and this is good type, bad type, and third thing is that in past you wrote water pen, it disappeared easily, but if somebody already not here cannot override, I cannot override, so just like that. This will appear a bit, it's a bit sad. So, thank you very much for Vasco-san's introduction, but I recently, from last October, I was actually started as Christopher Storage Chair of Computing at Oxford University. So, Christopher Storage actually have many inventions like computer game and literature and music, and unfortunately also he passed away very short period. But as you know well, he opened the field of semantics and theory and practice of programming language. And he said actually many manuscripts, he said very interesting things, in particular fundamental concept of programming language. Actually, types are not just boring Boolean or character, but types are very rich mathematical objects and abstract the computation, and he invented rich data types and polymorphism. They are very basic now for example, advanced object-oriented language. Without him, we are still writing spaghetti code, and he invented also, promoted structured programming and invented high-level programming language. So, what is a session type? He did sequential computations, but session types are for concurrency and communications, and promote the structured programming based on the notion of protocols. So, here today's talk. So first I talk about the origin of session type using Kohei's slide, and in particular focus how he moved from dyadic to idioms for interactions, and it shows a correspondence with linear logic, And types 4 also move to the distributed and concurrent system. I'm sorry, I have type here. And then we go from the web service to cyber infrastructure and programming language and system, the journey. And today I want to talk about a bit princess of session types. Who is princess? I will talk later. And also I want to show 5 session types. 5 people are so interested in steel from my viewpoint. And I will give some future direction, but last point I'm sure everybody will talk today a bit. So I want to first show Basco awarded for this ESOP 2000 ESOP paper for DAX test time award. We also got with Marco multi-party session types. Also, it's a bit hidden, but Kohei also got another test time award from Leaks based on his work about fully abstract game semantics for general reference. And this is with Samson and Guy Lancaster. And game semantics actually very important notion for him to form the core of the idea of session type. So I want to include his slides. And before that, I really want to always this kind of things at the end, but I want to spend a very long time to thank you, Simon. So this is Betty, and Betty is the cost action, and that is really enlarged session type community, and Kohei was actually quite excited. It started, and then he couldn't, of course, join. But I really want to say thank you for Simon beginning. And this time, actually, from Lisbon, when we have the last time Betty. So why session type? So I will start from this idea. So programming language is the tool to offer the framework for abstraction for various activities. In particular, promoting and important thing is limiting. And if you may want to promote imperative, or you may want to promote functional programming, also you may want to promote logic programming. And program is actually prescription of computational behavior based on a certain abstraction. So, what is a programming and programming? So, fundamental element of PA, actually this is Kohei's slide, and in this context is set of operators. Operator imperative, we have assignment and jump. Functional, we have beta reduction, and logical, we have unification. And another element is how we want to combine and structure programming using imperative. For example, you have while, sequential composition, functional, application, and recursion, and so on. So, this is unstructured quick sort by Tony Howard, and this is written by assembly language. And you can hardly see this is quick sort, and because it's not structured, we have got it. But if it is structured like this is a Pascal, actually, written like this, you can see, of course, this is quick sort and written like this. So this is imperative version. And if is a quick sort. But if you write combinator, you may be able to understand if you know combinator because you have y and so on. Concatenate like this. And however, it is better to return MN, and this is standard MN, and you using pattern matching and that and filter and these function give definitely you can now understand this is quick sort. So you can promote the function in functional language. So also observation is that now what is a pi calculus? So session type starting point is theory of types of the pi calculus. And his argument is that pi calculus can represent many things in spite of only few BNS. And few BNS is that lambda calculus, of course you have only 3 BNS, variable abstraction and application, but pi calculus case, you have another 3 and actually prefix like this, and input and output, and so on. And this part, encoding of lambda calculus, will appear again, but this is a Milner's encoding. Will be Milner's encoding. He wrote the lambda calculus in pi calculus and then proved correctly. But you can basically embed the lambda calculus into pi calculus by combining name passing. So, what is the function and interaction? So, function is the like this. You are very modest person, and then you have input and output, and you can compute in the sequential order. But pi calculus is more interactive and chaotic. So, to understand this, what do you have to do? But mainly, you can encode the lambda calculus in the pi calculus. But what are the class of interactive behavior? Rules of the interaction which you can express lambda calculus or other things. That is the view of this. And another thing, the good thing of the pi calculus, and you can think about it. So this is the applet, and applet, I don't know you understand what to mean applet, but you can think about it like JavaScript. You are sending code to other people. So in Java, if you send an applet, and if disaster happens, you can just have a disaster, and you cannot analyze what is the cause of disaster. But in pi calculus, if you can encode it, you can analyze more fine-grained. So writing pi calculus also gives a way of writing, understanding what is a bad behavior happened. And this is a big picture of the pi calculus and realm of computational behavior. So he believes you can encode anything in pi calculus, and pi calculus is great. And what you can see here, interesting thing. So pi calculus, of course, you can encode higher order pi calculus, of course, and you can see some language which is not now in the present, or not use Cobra, I don't even know, and Java beans and so on, and all basically can be encoded into the pi calculus. But this is not only he has done work. So, and that period around the beginning or later 19, many people start to encode various computations into the pi calculus to understand and expressiveness of the pi calculus. This is a very important there. And then, what is the role of types? So, role of types is that how you can classify message passing interactive behavior into the pie calculus. What is the class of the types of the behavior can we find in the calculus? And then safety is this program safe class of behavior? Can safety is preserved compositionally? And that would be the role of the types of the pie calculus. So, types of the function is like this. You have back, like this, successor, and is 0, and natural number, and you have operator, and you can see bool, you have back of the operator, and function, and not, back of the operator. Then, operation of the lambda calculus is application which is abstracted by types of the functional composition of the types. This is the functional types. But what is the types of the processes? Basically, you compose the channel one by one and check this channel composition is correct one. And if it is correct, you can get good process. And if it is composition, this fine-grained composition is bad, you will get bad process like divergence, deadlock, and runtime error. Therefore, we should prohibit such bad things when you compose channel of the interactive point. So now, journey to the session types is like this. So let's think about simple ATA. And you have the option withdraw, and I have only option withdraw, but you have deposit and quit, and you can see the balance. And this person put, probably this is a card, and interact with ATA. Then, if it is okay, take your money and then try again. Then, backward, there is an interaction with banking system. So, how you can represent such kind of distributed interaction as types or pie calculus? So, if you implement structure, this is a bit beginning part, like beginning form of the session types you can see now. And you have the label here, branching as pattern matching, and nested, okay, and you have recursions and APA. And I won't go to detail, but if you write this in the pie calculus, of course, this is ATM. If you trust him, but actually nobody understands this is written for ATM program. So session type gives such kind of structured interaction. That is the really form of the session types. This is also, I found the slide from cohesive slide, but this is also the, I can see we have sequencing and we have branching and so on. This is the form of the beginning of dyadic interactions. So now we go back. Second point is that, so we back from these pictures and people start encoding many computations into the pie calculus. But there were problems at that time. They are operationally sound abstract. I will explain later, but basically they are correct, but you cannot totally prove correctness. So, what it means, I will explain here, and I will focus lambda calculus, of course. So, I want to encode lambda calculus into pi calculus. So, this square is a mapping, and contextual congruence is defined by context and operational observation. And I won't go into detail, but probably next slide I have, yes. So what it means in the pi calculus, you can, encoding sound means that usually if encoding is correct, M and N are equated, original lambda calculus can be equated. So, which means that if P and Q are omitting A and M and N is omitting observed A as action, and for all contexts, this I wrote this one. And this direction is usually easily proved if your encoding is correct. You know, your programming in pi calculus is correct. However, this direction very difficult to get. You cannot get naively. Why? Because lambda calculus is big, as I showed in the slide by Kohei of Java passing. And pi calculus is fine-grained. So there are many bad processes try to destroy this equation in the environment. You can find such example in the Robin Milner's function as processes. The example, basically you can trick lambda calculus to prohibit to do good things. And context is a problem. So how you can do it is you can do typed bisimulation, typed behavioral equivalence. So what it means that types can restrict to the good environment. So good environment means that you can reject such kind of bad process from the environment. So this process destroys the equivalence, but inside environment you can get to the equality. So equivalent becomes coarser in the if you use types, because you are prohibited bad process. And this is a very good way to do it, because you can prove the also correct, not only prove correctness of encoding, but limit the environment, and this way you can prove compositionally. So now I go back in our around 1991, beginning of 2000. So at that time, we try to solve problem using the basically at that time game semantics actually is still very active area, but try to prove fully abstraction of the sequentiality into the domain, of course, domain theory. So using their technique, we thought we can try to prove the full abstractions of the encoding using the types of the pi calculus. And this is just a slide. We thought about what is the type game semantics. This is called by name game semantics. Start from opponent answer, opponent answer. And basically, game semantics quite similar with name passing. And there is a causality you can represent in the pi calculus. So So pi calculus can represent this, and game semantics can also represent this. So he thinks we can use this technique from the game semantics to prove the full abstraction result. So he gave some lectures in France. Try to do French lectures, I remembered. And at that time, Highland and Robin Milner were there, and Highland gave all lecture in French, so it was quite impressive. And unfortunately, I couldn't understand what he is saying, but yes. So he gave some lecture how to encode fully abstractly sequentiality in the with the game semantics and pi calculus. And this is the actually view and bracket condition represented by causality of name and action of name. And this is a function. And you can give some bracket. And as you can see, bound and questions and up and bottom and like this is quite resemble with the linear logic based session types. And however, we had some typing system. Actually, we could prove fully abstraction from TCA and also simply typed lambda calculus, sum and product, and system F, but unfortunately, game semantics quite involved, and it was very, very complicated. But there is a good news here, and we can actually use the process and proof. And this is actually some of lectures. And actually, linear logic can give us some form of the interaction already known by the forms interaction net. Basically, view of types for a dyadic interaction is types are interacting, dual are interacting, and symbol are interacting, so that you can reduce to the safe communication. If we can realize this as types, probably we can get to good types. So we are talking about this direction. It usually happens. And now, actually, it was much, much better solution were found by Frank Fleming and Louis Caires, and also later classical version by Philip Butler. So basically, if you have linear logic based session types, you can encode system F fully abstractly. Why session types could do it, I will explain later. And also you can get reverse directions also easily, and you can get this is a bit surprising result. And you can also encode session linear logic pi calculus into lambda calculus fully abstractly. That is a bit. And also you can prove the reverse. And I think I now find out I don't have much time, so I will skip and tell what is the essence of why we could do that. So this is the target. So session types different is this. So when you encode lambda calculus, you can encode variable in the linear logic version of this kind of order and nil to nil and like this. Difference is actually lambda abstraction and applications. So I go back to Milner's encoding. You can see it's much this version, linear logic encoding, is much clearer than this Robin-Milner's pattern. So Robin-Milner's pattern, when you get to it, because you have no continuous action like session type. Session types can do the action using the series of action using the same channel. But Robin-Milner's encoding, you cannot do it because you need to pass always continuation. This breaks the full abstraction. But if you look at this, encoding into linear logic pi calculus, you can see this name A is used again so that you can guarantee sequence of interaction very beautifully into the session types. That part of, and also correspondence allowed to encode also linear logic pi calculus into lambda calculus. So encoding is, this is pi calculus and this is lambda calculus, variable encoded to x, and you need always assume name, principal name A. And ax dot p, you can erase A, and you can erase type variable like this. And application is also just composition of two processes. I'm not going to detail, but you can also represent by substitution. So in this way, we can prove inverse and full abstractions. And I skip this, but summary is that with this result proved with Bernard, means that pi calculus, session type linear pi calculus, can encode it and encode functions. This looks a bit sad, actually, because linear logic based pi calculus is same expressive power as system M. That sounds bad. However, it's not, because this gives a discipline of, we know session community, we have good discipline of the types of the pi calculus, at least functional part, and based on linear logic, and articulate border computation, and moreover, too many to list, but for example, Stephanie's work and Jorge's work and Luis Caires' work, we try to extend this linear logic-based lambda calculus using more construct. That is a good attitude. So I didn't have much time, and unfortunately, but I have still time, like 90 minutes. Sorry, I should not so hurry, but this is what I have to. Okay, I'm forgetting my time. Okay, so now I'm going to move distributed and concurrent system finally. But I want to say really participation from linear logic people into session types is a great expansion and achievement, in particular functional community. And I want to really thank Frank for the discovery of these connections. And so, anyway, so next I go to the distributed and concurrent system. So we started multi-party session types from web services, and then we applied to big system, and now applied to programming language. So, however, computation are ubiquitous. Now, way to organize system and computation are based on many, many things articulated also by using communications. And not only this, industry people start to use and design the programming language which has explicit message passing protocol like Rust and Go and also ERAB, also microservices. So, when you want to write program, a protocol, but we face the problem. basically written always English, and also like this, and like English like this. If you want to implement SMTP protocol, which is meant to be simple mail transfer protocol, actually it is English you should go through, and it is 90 pages. So this is very ambiguous. So first of all, if you want to write a protocol, it is very ambiguous usually. Another thing is that, for example, as we know well, communication always causes problem. So look at Go language. It is now very major after Google designed many industry using to programming very big distributed systems such as Docker and Kubernetes, and there are many interesting discoveries in industry people, for example, like Uber, and they analyzed Go microservice and 2,100 in their companies, and they find out this Go language has causing quite a lot of concurrency bug. But what is a concurrency bug? So, as you can see, deadlock and channel error, and they analyze more than half of concurrency bug. Actually, not so much people are doing lock and unlock problems these days, but use of the communication or combining of the communications. So, our aim in this community is that we can probably use session types, and session type can prevent concurrent bug, and session type can abstract, implement, manage communication as protocol, and because session type is types, it's much cheaper than verification, and clean, it is simple, and also important thing is retrofittable to the programming language because of types. So this is a brief history of session types, and actually not the session type, multi-party session type. And as you know well, first session types, I think first full session type is discovered and actually invented by Vasco and Kohei and Kubo, and binary session type, which has derivation as theory of the typewriters. And actually, it has not been used for a while, and there are studies in the typewriters, but not used. But we had a good chance come from Robin Milner. He invited us, Kohei and me, and Marco, to join W3C standardization group, and where I proposed to use session types, because session types probably only the typing types they can understand. And at that time, actually, this is a hidden hidden part of a bit our group, but actually there is Petrinet people who try to push Petrinet and saying that our group, Phi group, is humble, and we should not use theory of the Pi calculus for web services, and this make Robin Milner very worried, and he created PetriPi working group for web services and try to sort out this kind of conflict between Petrinet people. And this is a message, actually, email I found out, and Robin Milner sent to Steve and me and Kohei. And this is email, but look at this email. Very, very, very. It's very difficult to say. It's very written very nicely, but it's really kind of like this. So this is going to Steve Ross Talbot, who was the chair of the web service working group. Thanks for that. I believe the PyCalCast team ought to be able to do something with it. You seem to be taking it in that direction. This is before we participated in that workshop to, meet people and prepare the use case for written in the PyCalCast or also Petronet. So we have a bit exchange workshop with them. And then he wrote this kind of message, and we have model use case, and also I will try to do it, and we agreed. I don't get these days, this kind of email from everybody, and I'm very honored to get this email from Robin Miller. But he was quite worried and serious. So, resulting of that CDL is choreography description programming language. And this was actually form of the collection industry people. And this is original choreography language. And this is Hello World protocol. And it was very, very complicated. This is Hello World protocol, but first written in the XIII. Also, Marco knows it, but we have many gathering industry people from IBM, Apple, like Red Hat, like this. And at that time, everybody want to say something. They want to put their idea in the standardization. So types getting extremely complicated, like role type, participant type, relation type, channel type, like this. And you can hardly understand this is a Hello World product. So Kohei started scribble programming language by saying scribbling is necessary, like this. I'm not reading this comment, but so scribble is basically essence of the choreography language, but more like abstract version of choreography language. So with scribble, you can write hello world, you have two roles, hello from you and world, like this. Now, after that, actually, we established, or we have come up the idea of multi-part session types, and basically we translated their idea into types of the PyCalCast. And we started Scribble project with Red Hat. And then we apply session types to the large cyber infrastructure, OI, and also some middleware standardizations. And I want to talk about a bit now history of the Ocean Observatory Initiative. So Ocean Observatory Initiative, what we achieve, we collaborate, is a very, very large project and historically large project, and build a cyber infrastructure for just observing ocean around the world. And basically, you can have some kind of equipment like satellite and, like this instrument, and get the data constantly, and then get the data and high-speed network and transmit and use these data. And this is the ocean, and you can see ocean is very actually active and observing ocean, not only this sunlight and also dust and water cycle, circular like this, heat like this. You can get all from ocean many, many important information so that you can predict, for example, global warming. That is their aim. And this is the cyber infrastructure, and get data, transmit, and then kids can use to develop science project, education and use, general public. This is actually Ocean Initiative A. And this is the cyber infrastructure. You can see many messages, and you need to manage this cyber infrastructure interaction so that we have aimed to join. So this is the actually San Diego, and they have also harbor to observing oceans, and I went with Ray and Rumi together to visit them, and very nice weather, and they like ocean, that is. And they stored in the equipment, and you can see it. And this is the evidence. We go to work to do the session type, not swimming or something. And this is Rumi, and this is they and me, and that is the time we observe. And you can see, so they are writing, ocean people are writing this kind of development diagram, which resembles with, of course, message sequence chart. And but it is very ambiguous. Where is branching and where is selection? They don't care. They just write this kind of ambiguous specifications. So what we do is that we write this in the scribble language, which can write this kind of protocol concise way. So you have role, 3 roles here, and choice, and nested choice, and recursion. Now write this kind of scenario very simply. And this can be projected, and this can be projected to automata state machine. That was what we are doing, developed in the scribble language. So, but actually going to see what's not important. Important thing is that after that, our community realized, oh, session type can easily integrate it with many different languages. So that is the things we realized, wow, important, and not only us, also not only limited to multi-party. Many people started integrating various languages. For example, last, we have the version by Antonio, and we have a version, and Stephanie, like this. Some language even implemented different kind of session types. So, briefly, already Marco explained, but session types are easily. So, first step is write global types to represent this interaction, like buyer 1, seller 2, buyer 2, like this. Then you project to the each end point, and integer and character, and then step 2 is project to local type. And then from here, there are many ways to use session types. First, you translate to state machine, and use this state machine to type check programming or generate code. Generate code, generate API, and also you can check, runtime check, communicating behavior. And you can use it. Another way is, of course, we can think about it. We can infer the state machine, and then build the global type, and in this way you can do the refinement and develop the software development life cycle. So we project, generate, refine, and building, generate, refine, building. This kind of things are very useful if you can do the incorporate with the testing. So now I want to talk about princess of session types. And who is princess of session types? When I saw the abstract of ST30 I thought somebody is missing. Who is great contributor? I think everybody know now who is she. She is live researcher, and she want to always say something, and she is really head author of this time PPDP, her paper. Of course, Mariangela Desani, I want to talk a bit about her contribution in this occasion. So, I met Mariangela in ETAPS 02, and this is a photo by Crow in Barendrich's book, and I have this kind of imagination. But when I met her, I understand she is a very nice, approachable person, and very kind person. But I was very stressed to meet her because very great lambda researchers in Barendrich's book, and actually she is only female in his Barendrich photograph, so that shows really her contribution to the lambda calculus. But I have also good opportunity to visit her home and stay her home, and I saw she wears actually mini skirt, and I see with Giuseppe, and that is also honor of this. And first time I met Mariangela, and she visited Imperial College. Of course, she has always collaborated, and many collaborators in the Imperial, but among them, we started collaborating with Sofia Dorospo, who is the really, Java expert, and with my PhD student, Demetrius. And they collaborated very nicely, but I found out, and we have TGC and eCoop 2006, which has the first formalization to mainstream language integrate session types in Java. But actually, I found Sofia and Mariangela has a very strong opinion and quite fight it to complete this work. And after that, we have also collaboration with, this is Mario Coppo, if you realize it, and first asynchronous session types. And actually, this very contributed, this theory is contributed to first integrate session types in mainstream language Java, done by Raymond Hu. And this is actually implementation of the binary protocol, and this is designed following by our paper at eCoop and later published in the I&C. Another her contribution is she always very good at simplify original theory. So original theory, popular as Marco explained, there is a channel in that script. This makes quite a bit of work to check linearity and so on. But she is very clever, and she has a way to much simplify multi-party session type using no channel, because she realized if we have FIFO communication between two parties, you can use this as channel. And so that her also contribution to simplify multi-party session types. And this is actually version currently implemented in the multi-party and in particular script. So actually we have global progress papers in the Conca 08, and she always brings many Italian collaborators. We have a bunch of collaborators here, and also we have inference of global progress. And later, our hero, Luca Padovani, joined with her to do the MPST of gentle introductions. And she is really live researcher, and she is always doing first things of the multi-party session types, and for example, information flow and security with Ilaria, and reversible computation, and also preciseness. Many things she has done first, and she is very active still, and we really have benefit from her. So now I want to say 5 session types. So actually very good. We have a bit of talk today about subject reduction of the session types. So I feel session types is very tricky. If you miss something, you have always bit problem. And one of the things is that delegation of the session types is very difficult. And actually, this is Honda Basco Kubo paper, original paper, and there are 3 interactions of the session types. So first, shared channel communication, which establishes the session with at the shared name A. Another communication is for practical, we send value via session name. Once communication established, you can send and receive with the series of channels. And also, it's very strange 2 rules in the original session types. One rule is that instantiation of channel or value, and another one is delegation. And this delegation rule of the original rule actually very strange. You have restriction here and restriction here, restriction here and free channel here. And this input and output have same channel and disappeared channel. And if you see this, it feels strange why they are doing this like this. But so natural idea is we instantiate this endpoint to the queue and substitute this. And so this actually causing quite a bit of problem. And actually, it didn't work for subject reduction. And actually, why I'm mentioning this is Mariangela found out this problem and informed the author and actually Simon and Basco and Antonio's paper. And so counter example is very tricky. Actually, if you just pass session name and instantiate it, capability changed. So this is a bug of this. So you can send this channel K dash is session name and instantiate it, and then you can get this. And usually session type should have session environment and subject reduction. Should be said that this instantiate this, you can get a completely different protocol because K dash is instantiated here and passed to it, and K dash have different session now. So you can get compatibility error and type is changed and not intendedly but unintentionally. So that causes the problem, and you can see immediately this leads to the counter example. So actually, what you can do is that, so why this problem doesn't appear in the original Basco and Cohe's paper is that they first alpha convert this channel to this name is alias, and you can alpha convert easily and in the pi calculus, and then you can pattern match so that you don't have this problem because this K is matched in the bound session types. But this is a bit weird. And actually, interesting episode I do remember with Simon is that Simon already realized this problem. And he had Iso paper long, but actually he already knew the correction of this, his paper. And actually he had invented polarity, 2-point of channel, and plus and minus, and instantiate plus and minus to the channel. So you can get this, keep this duality without aliasing and transferring the channel capability. And actually, they do mistake at concur paper is recent, actually after that corrected is that Simon forgot he corrected his paper that I don't know you remember, but that is the and now we are looking for the talk by Simon and Basco's book is using 2 endpoints. They don't have this problem because they have 2 restricted channels. So this is interesting things and how they changed. And basically they have this joint curve. And then they can use balanced 2 ends of channel are dual each other. And then you can prove this kind of invariance so that you can also prove the type safety. And these tricky things we realize is that programmatic. So later, and with Francesco and David, we mechanized this correct version in the code to prove correct. So another big mistake is actually subtyping. And this was actually me. So I talked about Simon's work, but Simon's work is not incorrect at all. But after that, we had global typing for asynchronous commutative sessions. And actually, I want to mention again about Mariangela and PPDP did the preciseness of subtyping asynchronous and synchronous session of the binary. And at that time, we wrote, because already Simon has the algorithm of subtyping, algorithm for checking the synchronous asynchronous subtyping of present paper can be easily designed. Actually, that is not correct. And now, joining communicating automata people. And this is to buyer and seller session types. I'm not explaining this buyer and seller communicate together and recursion and OK and retry and recursion. Actually, same form of the session type, assuming asynchronous communication, already discovered before session types. Basically, our session types is limited to 3 ways. First, deterministic. Deterministic means that 2 communications of label, if you go to different label, it has different state. It's not this. If you use the same label, you should go to the same state. So this is a deterministic. We have a choice, but we have a deterministic. And also no mixed state, which means that one state is going either output or input. And also 2 binary session types are compatible. Compatible means that both interaction is dual input and output to each other. Interesting paper we discovered later is that in communicating automata, it was known that 2 compatible machines without a mixed state, which are deterministic, satisfy deadlock freedom. Actually, if you they just destroy one of the conditions, it's very difficult to get to decidability of reachability. So after that, this correspondence, actually we found some people also, communicating automata people are joined, and we believe the asynchronous subtyping is decidable, but actually proved in the this framework, communicating automata or pure automata system by Marco, and proved undecidable. And that is leading, actually, good to think, is connection with automata theory and session types. This makes different also another community. Another thing is a multi-party session types. This time, I want to bit correct some incorrect argument about our paper with, my paper with, I hope I can explain better this time. So, Alcesta and I had a paper at Popper and arguing this is true, plane projection of global types has no issue for proving subject, but mergeability using the session type paper with more flexible mergeability is actually have a problem proving subject reduction. However, I want to, this occasion, want to correct it, and this is a bit, I will back to this. Okay. And so, this is a diagram to show the relationship between the projection with no mergeability and projection with mergeability. So, original paper, projection, I am not explaining again because Marco did a good job. And this original paper by multi-party is very limited and but state consistent. And mergeable global type is actually state in both liveness, live plus, and deadlock freedom and safety, so that this generates sound actually endpoint. Only the problem that paper is that. Problem in my previous paper is that. Actually, this is the invariance of the subject reductions of the pi calculus and session pi calculus, multi-party session pi calculus. So this consistency, invariant consistency, does not hold if you naively define what is the consistency of the local environment. However, you can have different way to solve the this mergeability problem, not mergeability problem, still using mergeability. We can just enlarge the invariance of this consistency to prove the subject reductions. And actually, first time we did is that before we know it, and with Onera and Alcesta and Ray, we have using consistency and basically double projection defined up to subtyping. Then you can still ensure the consistency and prove the subject reduction. Another way, also using Simon's recent paper, is that we use projection but use the invariance for safety property. So still you can use the global type and mergeability but can state the subject reduction. Another way is using association similar with Markov between the global and local types, and use, so there are many other ways to prove, I forgot this, yes, and global types prove that. Also, Ilaria is talking about this, and use global types to directly type multi-party session process, defining global semantics. This is another simple way to prove the subject reduction. So there is a many way to still doing mergeability problem. That I wanted to bit correct it. And I go back here, this slide, because of this relationship with communicating automata. There are many interesting and also expert joined in the session type community, which enlarge also use of the model checking for the verifying session types. And one is actually, Marco's team and Mario and Gianluigi, and have some asynchronous subtyping, and also global analysis, and also bottom-up approach is also applied not only PyCalculus, also other programming language, Go and other things, Rust, like this. And also, we have now experts from higher order message sequence chart community, and we are looking forward to the talk this afternoon. And actually, I was very surprised to see this paper's result, because we have kind of global type and completely sound, and I know we can map to the sound, but completeness is usually quite difficult, because we have completeness up to asynchronous subtyping proved with also Sabia people and Alchester. But up to asynchronous subtyping completeness means that we have undecidability to do this. But this cover paper is actually shows a sound and complete projection from multi-party session type. So this is actually quite a surprise result for me. But today I also learned from Marco's talk. So we have many interesting challenge in the session types, because it's quite subtle, in particular with asynchronous. So now, I'm sorry, I go back to very technical things which I want to talk, but future direction, I will probably leave to the panel discussion, but many things probably, I can pick up one thing already discussed. Mechanization should be pushed forward more, and also we should have good benchmark set, and actually today's paper, this SPLASH is already applied session type to real distributed system, and that is very good attempt. And foundations, I think I want to mention one thing. So typed behavioral semantics, which is actually, I go back to the slide with Kohei, and when he compare function and process, we have types and programming language, but actually function have very rich semantics and category semantics and so on, which we don't have much study in this community. Probably, why is that? I believe, except probably linear logic people, we didn't much study about typed behavioral semantics. If we don't have behavioral semantics, it's a bit difficult to analyze what is the equivalence of the session process. So we have very good success applying session types to model checking and also programming language. But I want to mention my work a bit about we used global type for typed by simulation and investigate ocean observatory protocol and induce different semantics. These things probably can be pushed again. So I thank Simon to read Betty again for last slide. And also I hope we have very good already. I feel very good benefit to attend this workshop, and Thank you very much, and let's have a good discussion during 2 days. Thank you.
So thank you so much for this talk. And we can take some questions from the audience.
Yes, thank you.
This is not a question. Thank you for the wonderful talk, very touching at times. And since you very nice tribute to Mariangela, you proposed to call for the princess of session time. I propose that we call you the queen of session time.
But why I said to princess is, Kohei said Mariangela is like Ojo-san. Ojo-san is a bit difficult to translate in English, but she enjoyed by herself, and rather than queen or mother, she is very active and she has opinion and she is leading, so I feel she is more like active. And yes, a kind of a bit selfish, always saying, well, I want to do this way. So that is the reason I said princess. Yeah.
I'm curious if I may ask. I'm curious that because I was not part of this multi-party series. So, what exactly was the if you go back in time, and what exactly was the trigger to go beyond binary session types?
So trigger is that there is a request from industry people, in the choreography people. They cannot ensure deadlock only for 2 parties. And you need, we have probably way to solve to checking name circularity and so on, but they want to first write this protocol, like I demonstrated in the oceanography. And they always write development in the UML diagram, and they want to realize in their language. So that is the reason trigger to the multi-party. Yes. So endpoint projection. But the endpoint projection is from their idea. So without this, we didn't come up with this.
I have a follow-up on this. I've been wondering about this for a long time. I do know that in relational databases, when you have entity relationship diagrams, which you use instead of the analogous thing to UML, there is also a discussion, and there's some papers where they say there's a difference between restricting to binary relationships or n-ary relationships. And I was wondering whether you know more about that connection.
I'm not the expert of database. I don't know it. So probably it's better I know to give a
I think it's really interesting because
yes.
I think it's related to the distinction between binary and multi-party. And Mora Nori, she was a database professor at ETH. She, at the time, we had a conversation about this. So, but anyway, so I think it's actually interesting to look into that.
Yes, I skipped one slide, but with Bernard I proved another thing which is probably quite related with Kirsten's talk tomorrow, and about bit distributed system. So binary connection basically in particular linear logic, because when you don't have shared channel. So multi-party have this kind of, can represent this kind of distribution connecting ABC at one point. But linear logic one, you can connect AB restrict, BC restrict, so that you cannot get this kind of diagram at the same time. So this is also related with expressiveness of the difference between distributed and localized. Yes.
Marco?
question. How do you see in 10 years session types for users?
I think quite, first of all, a very good thing is still we are quite going to integrate session types to the programming language. That should not stop. And another thing is that we are discovering very subtle point of the session types, which is very interesting. And we should, I think it is continued. And I hope we will enlarge the community. Now it's getting quite a large community from experts, but we should try to encourage to expert. But 10 years, I think we are still doing session types.
Are there any further questions?
Just maybe an additional remark about the motivation for studying multi-part session types. I think there has been a proposal by Jorge and Luis to encode actually multi-part session types using binary session types by introducing a kind of mediating participant. And so that encoding works, but it doesn't preserve distributability somehow.
Yes, so this is needed.
So I think it does make sense. It's natural to want
Yes,
to do that.
distributability is one of the way to measure the difference. Yes.
Yeah, but I just want, thanks for, thanks for, no, I mean, I will talk about that actually in my talk, but because I don't consider that an encoding, but of course it's something that adds to our understanding about how different things can be related, but yes, it's one way of thinking about that, but I don't think it's an encoding in the sense of encoding as we would normally think of it.
Yeah.
Thanks for that. Self-promotion.
So, any further questions from the audience? So, now for
Yeah, but
Yeah,
it's,
it's gonna show. Yeah.
okay, great. Works.
Yeah.
Great. Thanks.
We still have a few minutes. So if you do an example, you have a very clear idea of what you want to convey, right? Yeah, it's very
Who's the chair for this session? Who's the chair again for that session? Yes. Because it's a bit. Okay, yeah. I guess he noticed he can be as late as he wants, right? Yeah, he's not here yet.
So we're waiting for the chair.
We are. Did you see him on the way?
No, I haven't. And he was not upstairs because I was there with him. You don't want to sit in the front.
So, welcome back. Speaker is Felix Stutz, complete multi-party session type projection with automata. Go ahead, Felix.
Thank you, Simon. Yeah, so I'm Felix Stutz from Max Planck Institute for Software Systems, and this is joint work with Elaine Lee and Thomas Wies from New York University, as well as Damien Safri from Sonasource. So we've all seen today that this should work, and it does, but with some delay, I'm sorry. So in this talk, I will represent global types in this visual fashion because I usually do in presentations. I expected here you would have understood all the syntax, but in some audiences they don't. So this is a global type which represents a load balancing protocol, represented as high-level message sequence chart. We start at the top. There's a client C who sends a task to the server, and then the server distributes the task to one of two workers, either the worker W in the left branch or the worker U in the right branch, and then it sends the result right back to the client, and then it recurses. You've all seen something like this. I just want to give you this idea. Okay, we're in this model, multi-party session types. We take a global object and we want to produce a local object. And how do we do this? Usually it's projection, right? And here, I depict projections as finite state machines. So this is the local specification for the client C, where it starts at the top, S!T. I don't need to tell you, that means that C sends the task T to the server S, and then it receives the result either from the worker W or the worker U, and for conciseness, I didn't merge these states for readability, basically. So let me be a bit more specific about the model for our local specifications or local implementations. As Marco pointed out, we actually do not use local types, but we use communicating state machines, which are a standard model for distributed computing. So introduced by Brandt and Safri 40 years back. And we do so with channels, so we are in an asynchronous message passing setting. To be precise, the programs or the specifications are finite state machines rather than push-down automata or even Turing machines. And our channels are point-to-point, so a participant can decide to send a message to exactly one participant rather than just broadcasting it over the channels. Capacity is in theory unbounded. We consider reliable channels, so no lossiness or anything like that. And the order between, like for every of these channels, which is like one between each two participants for each direction, is FIFO ordered. Okay. Interestingly, this model is known to be Turing complete as established 40 years back. So what we consider in this paper is what we call the implementability problem. Given a global type, can we generate a deadlock-free communicating state machine with the same language? So it generates exactly what we wanted to specify with our global type. And for this particular example, we can generate the local specification similarly as I've shown before for the client, also for the server and the two workers. And this indeed is a deadlock-free communicating state machine that generates the same language. However, we all know that things can also go wrong. You cannot just take the projection and let them interact because they might either generate more or they could deadlock. So here, the reason for this is that in a multi-party setting, every participant only has this local view of what it knows of the global run of the protocol. So we have 3 participants, A, B, and C. A decides the branch to take, either left or right, by sending an orange or a purple message. But then B doesn't forward this information properly to C, it just sends a blue message in both branches, but C later should know which branch was taken. It's easily observable that this cannot be implemented because C will never know which branch was taken from the local view it has. So we can obtain a candidate implementation that looks like this. And here you see that C basically receives a blue message but then branches, and this is where you get into trouble, and this candidate implementation, and in fact any candidate implementation, will exhibit this behavior, where the participants A and B took the left branch, and C arbitrarily decided to take the right branch. So from an algorithmic point of view, we would like to distinguish between these implementable global types and unimplementable global types, like this one. And I wanted to depict this space of multi-party session types, or rather global types, with a blue box, and then in this there is this implementable blob. And this particular, like here for us, this means it's implementable if there is such a deadlock-free communicating state machine with the same language, and unimplementable if there just exists no such communicating state machine. And this is important for our notion of soundness and completeness. And I want to briefly recap what this means to us here. So for this, I need to show you what I have as algorithm results. So if an algorithm gives you back the tick, it says, oh, in my opinion, this is implementable. And if the algorithm gives you the cross-sign, it's not implementable. Given that in mind, soundness basically means if I get the tick back, then the protocol should be implementable. So intuitively, all the ticks should only be in the green box, in the green blob, and none of the ticks should happen for the global types that are outside of the green blob, right? If you think about completeness, it actually is here the opposite statement. If it's implementable, then it should actually also give you the tick, your algorithm. So intuitively, you can have all the crosses in the blue part, but you should never get a cross in the green part. So if we say that we have a sound and complete MST projection operator, the overall picture looks like this. We get the ticks in the green part, no crosses in the green part, only crosses in the blue part, and no ticks in the blue part. And this is exactly what I talk about. And I added an example because, Marco, you said something that I kind of disagree with a bit. You said that if you have 2 participants who are part of a choice, then any other participant should be notified later on. I agree with the notified part, but I do not agree that you need to have one specific message. Here in this example, A and B, again, take the decision. Like A takes the decision and B knows about it because of the message it receives, right? Like at this point, B knows, okay, if the message is orange from A, we took the left branch. If the message is purple, we took the right branch. Later on, in this loop, C receives two orange messages from B all the time. The difference here is in the first 2 blocks. Here, C receives 1 orange message, while in the right part, it does not receive any orange message. So at the end, once the blue messages arrive, which just indicate we're done with the protocol execution, and C should know which branch to take, the parity of the messages, of the orange messages, actually lets C know which branch was taken initially. It doesn't learn about it just by one specific message, but because of the semantic property of all the messages that appeared before. Okay, we can handle this, but I want to give you some more details on our setting. So I talked about asynchrony, and then we also know, most of you know about directed choice probably. This means if you branch, you have a dedicated sender-receiver pair, and only the messages need to be distinct and can be distinct. We consider what we call a sender-driven choice setting, where we only fix the sender, here A, and the pair of receiver and message need to be distinct across all branches. So intuitively, this means that you're allowed to send to different receivers, obviously, But if you flip that, it also means you should be able to receive from different senders. This comes with its own challenges, and this was actually what I will talk about in like 10 seconds probably. I enlarged here the blob of implementable protocols a bit. From my discussion about the soundness, what you intuitively want to achieve with the algorithm is to cover all this green space. So let me start with, and I know this is by no extent a full list, because I just said, okay, the first paper on multi-party session types proposed the projection operator, which is linear and considers directed choice. There have been multiple more papers later going from plain merge to full merging, but I don't have time to list all of them. What I want to say is that we basically start from this, and obviously this is a qualitative view, not a quantitative view that there's so much space around there, but I need space for my labels here. So with our Conquer work in 21, we extended from a linear to polynomial complexity to go to a sender-driven choice setting. And why do we need polynomial complexity here? Because this receiving from different senders comes with its own challenges. If I receive in the directed choice setting from one single sender every time I branch, I can rely on that FIFO order for that channel. But if I receive from two different senders, then these messages are not necessarily FIFO ordered. There is a partial order between these two channels. So I need to, we came up with this idea of a message availability analysis to account for these races and check if they're detrimental to learning about the choice. So this is the cost you got with polynomial, and it's cubic, so it's not like to the 10 or something. And we've implemented that back then. It works nicely, and it's like the overhead is lazy in the sense if you don't need the computation, you don't need to pay for it. Okay, but still, this doesn't cover everything, right? So in eCoup this year, I presented an X-space decision procedure for almost a full class of global types. Almost, because I require for every infinite execution of the protocol that every finite prefix of it can be completed to a finite completed run of the protocol. That's a side condition that I needed to show a reduction from MST implementability to high-level message sequence chart implementability. Still, this was not fully complete, so this is what we covered with a direct MST projection operator, and we also settled the complexity to be p-space complete. And this is exactly what I want to talk about here in more detail. So our approach consists of two phases. The first is we construct a candidate implementation, which is very similar to the first few slides I've shown you. You just take the global type and you just project it onto the alphabet of the participant you consider. I'll go into details. And then the second part is we have annotations on these candidate implementations that allow us to check two conditions. We call send and receive validity. And we've proven both of them together to be sufficient for implementability and each of them to be necessary, giving you completeness. So the first phase has two steps. Step A, we translate this high-level message sequence chart or global type into an automaton. And we label the states, which you can think of the global points of the protocol you could be in. And then the second point is you take this automaton and you project it onto the alphabet here of the client. So this is the load balancing protocol from before, I should have said. And you see that the first interaction projects to S!T because the client sends the task to the server, while for the next two, like these two, the client is not involved at all, so this is an epsilon transition. The subsequent ones are just receive points, and the errors back are again for readability. So now we keep track of these local points and we determinize the result. So you just do a determinization and you keep these labels of the global points in the protocol you could have been in. And intuitively this means that if I'm in this state as the client C, then my local view is compliant with any of these global states 2, 3, or 5. And these annotations we use in order to check these two conditions, send and receive validity, which are the second step. So first I want to give you an intuition what send validity means. Here we have an unimplementable protocol, which is basically the one I've shown you before, where things went wrong, just flipped top and bottom for space reasons. So A decides the branch, but B doesn't tell which branch was taken to C. C should know the branch. So let us construct this candidate implementation for C. You see, okay, in the beginning we're in T1 or B1, then we receive a message, we're in T2 or B2, and then we branch, sending an orange or a purple message, and we are then either in T3 or B3. And this always, as I've shown you before, exposes this execution where C thinks we're in the bottom branch while A and B think we're in the top branch. So that's the reason why we're not implementable. We can fix this protocol, and obviously this is not a fix for the real world, but for illustrative purposes here, by asking C not to know which branch was taken by just sending a blue message in both branches, so it doesn't learn. And then the candidate implementation looks like this. Here, there's one single transition from T2B2 to T3B3, and then the takeaway message for send validity is basically, if I'm in one state with an outgoing send transition, this send transition needs to be possible from every single state that I annotated. Otherwise, we've shown that this can cause problems. For the other operation, so receives, let me also give you a very toy example where, again, A decides the branch to take by sending distinct messages, and then both the subsequent interactions are the same messages, just in different orders. The candidate implementation for C looks like this. Initially, it's in T1 and B1, and then it can receive any of the two messages, and if it receives from A first, it thinks it's in the top branch. No, it should be exactly the other way around. I'm sorry, this is a typo. So, that's unfortunate. Yeah, basically, I don't use the graphics, but I give you the intuition. It branches depending on which message it receives first, but then it also determines the branch it took because the global, like the per participant order is fixed for the global type. And then this here will always expose the execution where C thinks it's in the top branch while A and B actually decided to be in the bottom branch. This is correct with respect to the left point again. So it's not specified. Intuitively, you can check this, that this confusion arises with these available messages I was talking about earlier. So at this point here, if we can take this receive transition, we should check that no other message is available from the other transitions, because then confusion can arise. So we can again fix this protocol here by introducing extra dependency, where C now actually acknowledges basically the reception of the first message to A here, not to the sender of the message, and then you introduce this dependency, so the message of the other branch that shows you which choice was taken for the other branch will not be available yet. So intuitively, participants learn about earlier choices through receiving, and this is why we need to check that these available messages are unique. So overall, we've shown that these two conditions together are sufficient for implementability. So if you take a global type, you produce the candidate implementations, you check both conditions, and they're true, then this candidate implementation actually implements the global type. And for the reverse direction, we showed that if one of the two conditions breaks, there actually is a counterexample to implementability. In terms of complexity, we've shown piece-based completeness. The upper bound is basically membership in piece-space, and with the earlier results, it suffices to say send and receive validity can be checked in piece-space. And for the lower bound, we use the reduction from NFA universality, which is inspired from earlier results from the early 2000s in the high-level message sequence chart literature. And notably, this result persists for the directed choice setting, so it does not need the sender-driven choice. We evaluated this approach against our own prototype and see that the runtime doubles, but it's pretty much the same order of magnitude despite of this p-space hardness result. And we've shown some of the protocols that could not be verified with our earlier prototype to be verifiable. In fact, with the completeness result, this should be true for any protocol that you feed into the prototype. For the proofs, how we do this, there are more details in the paper. And what I do not want to cover here in detail, you know, I've set implementability problem as this deadlock freedom plus same language. But our results actually entail a number of interesting properties that you care about for your system. So absence of unspecified receptions, absence of orphan messages, that every transition in the communicating state machine is executable, and so on. So to wrap up, I leave you with that visual that shows that we covered with this algorithm the implementable space for the asynchronous and sender-driven multi-party session types and showed this problem to be p-space complete. Thanks.
She already gave to me. This is really wonderful and shocking result for me, as I said before. And yes.
I think I could clarify on that a bit.
Yes, and so, but I had, so I think you are, so first cover paper, you use target is communicating automata, right? And there were your paper example which cannot be represented by local type syntax. Am I correct? There is a epsilon, you said.
Do you know which example you're talking about?
Not probably, but probably paper you have epsilon, so that, but it from your presentations. Intermediate state is actually only epsilon is using for intermediate state, and
yeah, but that's just an intermediate representation. The candidate implementation, like our state machines.
Because epsilon is not to be able.
But this is the domain. This is just an intermediate state that we use, but our actual candidate implementations do not use epsilon transitions.
Okay, so
yeah, but, I mean, yeah,
okay.
that should work.
Okay, so then which means that your concur paper actually translated to targeted local type, yes. Right? And but you change it to communicating automata.
Yes. We felt that this was more natural in this session, for this work. And we actually have an example where at first glance it looks like we produce something that is not representable as a local type, but this is not because of epsilon transition. This is because of some structural properties. Because if you think about local state types, they always have this tree-like structure. But we have ongoing work that shows that this is not a restriction, actually.
Okay.
So you can turn these things
to local type syntax.
Yeah.
Okay, I will.
Yeah, but I think.
But your paper said you cannot do local type syntax, but probably I'm misunderstood.
I don't think we claim that, to be honest. I think we claim that the classical projection approach would never produce something like this. But what I just claim now is I can produce this and I can transform it back into a local type.
Okay, thank you.
Which is different. May I clarify on your comment from your talk, actually? We do not employ asynchronous subtyping. We don't
yes,
do
I know
subtyping.
it.
Okay.
I know it.
Because
you don't.
obviously,
I know
if we
it.
did, then this would all be a bit dodgy.
Yes, no. But I found because
Yeah.
my work is, project and using subtyping, sound and complete. But your work is only projections, but complete. So not projection. In the case projection, but complete. So I'm very impressed by.
Thanks.
Yes.
Thanks.
I have more questions, but I have other people.
I'm here until Friday.
I saw Ray first, so Ray, go ahead.
Thanks. Sorry, no, just a very simple question. Probably I just missed it. Are there any restrictions on the protocol for your approach to work at all? Is it completely free-form? Anything?
Sender-driven choice.
Sender-driven. Okay, so
that's a restriction we cannot get around with this approach currently.
Okay, right.
That's definitely one. But I would say it's already a generalization to the director choice that is normally considered.
Okay, sorry, and just
so no mixed choice. That's
okay. So
to be very explicit,
right, no mixed choice, the sender-driven choice, but that one was two properties sort of rolled in. There's two sides to that, right? The sender-driven choice. There was.
Yeah, let me.
Sorry, I just missed a little bit.
No, that's fine. I can tell you that. I mean, we say sender-driven choice for the global types, right? We do not put restrictions on the communicating state machines, though. In fact, our completeness result shows, because of send validity, a corollary is that you don't need mixed choice states, which usually is an assumption in MST frameworks, but we show that this is actually a reasonable assumption. So if you take any protocol which satisfies sender-driven choice, you can always implement it without mixed choice states.
Okay, and sorry.
No, that's fine.
And your approach verifies the sender-driven choice. It doesn't just assume this.
I mean, this is just a structural property.
So it's a very trivial.
The prototype, I admit, does not check this, but it's just take the syntax, and for every choice, you check that the sender is the same and that the message receiver pair are distinct. I would say that's pretty easy pre-processing. It's a structural property. It's not like something. I do not say if you give me a mixed choice global type, I do not say there does not exist a sender-driven choice type that actually implements, specifies the same protocol. That's a different
you start from global types and then you transform them in global automata. Now, does your result only hold for when you start from global types? So actually you can get rid of global types. So you have more, because I believe the automata can be more complex, right, than a global type. And I think maybe also what Nabugo was saying before.
Yeah. So the approach, I mean, it takes the translation, but it doesn't use the fact that it's the image of a global type at all. Yeah.
So it holds for any automata, basically.
Small caveat, every final state needs to be sync, because that's a property of global types that you get always, right? So you do not allow outgoing transitions from a final state. So other than that, any, yes.
Say that again, has to be what?
A sync, no outgoing transitions.
I can ask very quickly. So you said you don't use asynchronous subtyping?
We don't use subtyping at all in this work.
Okay, that you answered.
Yes, we only produce it's ongoing work.
Yeah, so thanks for your talk. So there is one point that I think I already asked you in the past, whether what is the status of this notion of, in the syntactic version of global types, so global type is acceptable if it's projectable to every participant. I wonder if this has some status in your setting. So that's my first question. The second question is, can you express delegation? Because, or this kind of thing that for which you say, okay, it's nice to have a process calculi behind one thing is delegation. So can you comment on that?
Okay, yes. First question I remember, and that we also discussed. I think my answer didn't change much, to be honest. It's just the notion, yes, the notion of what is supposed to work. We do not use the circular argument that you define like the projection and then you say it's fine if the projection works. We say this is what we would like to achieve, which is a communicating state machine for this protocol. And then we have this only allows us to talk about our projection operator in relation to this property. Because if you define the property in terms of your definition, it's kind of a bit circular. Second point, again, is ongoing work that I just put into my thesis. So basically using this for type checking and also delegation. And yeah, because I just submitted only, and we will put that into submissions very soon.
But the sum is incomplete, so I mean, but you have to find what doesn't include delegation, because I was expecting to be expressible somehow with this.
No, this work does not include delegation. Yeah.
Okay, we better move on for the time. So thank you very much.
Thanks.
So the next talk.
Yes. Yes. So thank you very much. And so I'm talking about sessions. I will assume a lot of things since the community is an expert in sessions. So if I say something that you don't understand, that is not familiar, please raise your hand and feel free to interrupt me. So we all know what session types are, and so we need to codify this structure of communication, but usually there are some ingredients that can be missing. So there are a lot of flavors of session types, and in particular we focus on the need of what do we do if we want to broadcast something, what do we do if we have some signals that come, so how to react to those signals, and how to take care about time. So there are a lot of approaches that talk about physical time, and instead we went to a new programming setting, so synchronous reactive setting, that embeds broadcast, events, and concerning time, we talk about logical instance. So let me just give you a very brief introduction of what is a synchronous reactive programming. So we have a sort of logical tick that marks time, but it's not physical. So in this setting, we have that components are computing till they can't do anything more, so they are suspended. I will say what can they do and why they are suspended, so just follow the intuition now. And when they are suspended, then they pass to the next instant. And they are synchronous in the sense that they all pass to the next instance together, and they react simultaneously to events that can be emitted during the logical instant. And there is a new kind of property that is similar to progress. So we say that we can compute, so there is no deadlock, there is no, infinite loop inside a logical instant. So we can prove that each instant will terminate, will arrive to a suspended point. So what is the marriage between the two then? So it is reactivity and sessions. So first of all, we want that all requests coming from participants must be answered within the same logical instant. And the second thing that we want to have, we want to be able to react to events and try to execute an alternative protocol when we recognize that an event has been emitted. So again, some intuition on how a logical instant works in the session setting. So as I said before, we have these components, these participants, that they will compute until they cannot evolve anymore. So when they cannot evolve anymore. So we say that each participant can broadcast at most once. So if we have two send actions that are consecutive, it means that they need to happen in two different instances. What is the intuition behind this constraint? The intuition is that So we are sending a broadcast, so a message that is visible to everybody, and we wait till all the participants retrieve this message. Now, if a second message arrives, what is the meaning? Shall we erase the first one? So there are some policies in synchronous reactive programming where you can collect all the messages, and maybe you take the maximal one, maybe you take the sum. So we go for the easiest way because this is a sort of an orthogonal principle. So we say that we just broadcast once, and if we need to send another message, that message will need to wait the subsequent event. So it means we send a message, and then if we need to send again, we are suspended. So we cannot evolve anymore. On the other way around, if we want to receive twice, it doesn't make much sense to receive twice the same message. So it means that if we have already received the message from the participant that we are interested in, then we cannot evolve anymore to receive the second time because we will need to wait for the new value to arrive. We can emit as many events as we want. So an event will be signaling something that has happened. So, and we will use it as a way of branching in some sense. And then, when do we react to those events? When when we switch instant, then we will take a look at the events that have been emitted, and everybody, all the participants, will switch to an alternative behavior if the event was concerning the behavior of that participant. So, example that should be quite known to everybody. So if you ever used eBay, so electronic auction, we have an auctioneer that offers a good for sale, and several buyers that can compete on this sale, on this good, sorry. And the auctioneer will supervise the bidding and decrease the knockdown price. So some additional hypotheses just to make the setting easier for us. So we have one auctioneer and bidders, and one instant, one logical instant, will represent a bidding round, meaning that during the round, all of the bidders will send their bids, and the auctioneer will reply with the maximum. And as soon as a standstill is received, then the auctioneer would say, okay, we have a winner. And then some few additional hypotheses. So we have that the starting price is the same for everybody. Each of the bidders has a maximal budget, because otherwise we will have infinite loops. And these two hypotheses here are just for us so that we know who is the winner. But they can be relaxed but just by making the protocol a bit more complex. So what is the behavior of the protocol? So let's forget for a moment for the colored parts. So this is the global behavior. We have that each of the bidders, Bi to Bn, will send their bid to the auctioneer, and then the auctioneer will reply with the maximum. And the idea is at a certain point, we will decree a winner, and then we will end. So this watch construct that you see here is the way of interpreting this event handling. So there will be somebody emitting an event saying that the auction has finished, and when this event is catched, we will move to this alternative behavior where the auctioneer will decree who is the winner. So we have broadcasts, as I said, but from the point of view of the global type, they are actually just the usual multicast outputs. So we mark who is the sender and who are the intended recipients. And then there is another construct, there is this pause construct. So we will see that in the type construction, we will make the instance slicing explicit. So this pause means that every time we recurse, we stop the bidding round, and we start a new round at a new logical instant. So I'll just show you the implementation of the auctioneer. So recursion is the usual thing. We just need a parametric recursion because we need to remember what was the bids, what were the bids that we've seen before. But the idea is that if we receive the same bid as before, we have finished. Otherwise, we just communicate the maximum here. If we have reached a standstill, then we emit this event. We have finished. So this is this event. And in that case, at the next instant, all of the participants, so the auctioneer and the bidders, will arrive to this alternative behavior that is the end of the auction. And they will, this end bidder, so they will be notified who is the winner. So as you can see, the green, bluish thing of the emit is actually transparent from the point of view of the global type. So we don't care about event emissions in the global type, but they are present in the implementation. So summing up, what do we have? From the session point of view, we have input, recursion, these if-then-else constructs. From the synchronous reactive programming, we have the pauses. So the pauses are explicit way of saying, I finished computing, let's wait the next instant. The event emission, so we can emit as many events as we want. And this event handler that takes a role in the computation when we go from one instant to the next one. I put broadcast in the middle because it wasn't, it is a feature of synchronous reactive programming, but it's not just present in synchronous reactive programming, so it's something in the middle between the two. And from the type point of view, it's not really problematic. As I told you, we treat that as a multicast at the end, so it didn't change much the complexity of the typing system. So, what are the semantics? Obviously, we have a configuration where we have our process, as usually, the memory where we store the messages, so it's a sort of shared memory where the messages are stored, and we also remember who is the participant that sent the message and what are the participants that read that message, because we need to remember not to read twice the same message. And we have this environment E, that is the environment storing the events. Since we have this, not just the process reduction, but this passing of a logical instant, we also need a new kind of reduction, that is the tick reduction. So let me just give you two examples that are very easy, things that I will just point out, things that I already mentioned. So this is the reception rule. So as you see, we check, let me see if no, not working. So, as you can see, we just check that our participant is not present in the set of participants that has already read the message. So a reception can only happen if we haven't already read that message. And this is another interesting rule, that is the rule about recursion. And the idea here is that whenever we arrive to the recursive point, we have to finish, this has to be one logical instant. So we run till the recursion point, we pause, and then at the next round, next instant, we can resume recursion. And this is actually the key part to prove that we have bounded reactivity. Because if we didn't have this, then recursion can possibly be an infinite. So this is the key point, and that's why I wanted to put it out here. And this is also why we need to have that pause in the global type before the recursive variable. So for the tick reduction, this is a bit more interesting because it's a bit more unusual to the community. So the idea that I said is that we can compute, so the process reduction goes on till all of the processes are suspended. So they can't evolve anymore. What does it mean? That we need to be able to identify that all of the processes are suspended. And this is the role of the suspension operator. This suspension operator will check if there are two subsequent sent, so in that case we are paused, or two subsequent, or a pending reception, so we are waiting for a message that is not in the store, or an explicit pause. If we are in one of these three cases, then the whole network of participants is suspended, and therefore we can move to the following instant. So what does it happen when we move to the next instant? The idea is that, first of all, we will empty the memory so that we will prepare to the next instant and to the new messages that can be broadcast. We also empty the event environment, so we will receive new events and we can react to new signals. And concerning the network, the thing that we do is that, first of all, we remove all the pauses, and then we react to events. So what does it mean? Remember the watch construct? So for the watch construct, we just take if we find the event guarding the watch, it's just a try-catch, it's not so new as a concept. So if you find the event, then we replace the behavior with the finally behavior. So the typing system. The typing system, I won't get into details concerning communication, nothing new there. The things that are new are actually the event handler and the instance slicing. So the instance slicing is explicit. We need to mark all of the pauses in the global type. As I told you before, we don't care about event emission, but we do care about alternative behaviors. In some sense, it's a sort of an if then else, so we need to track the normal behavior and the alternative behavior. So to give you an idea, so the first one is a process that is suspended because it has to send twice. So when we type a process, we also need to carry on the memory, because otherwise we don't have any information about what are the messages that have been sent and what are the participants that have already read from a process or not. So in this case, as you can see in the memory, we have that the participant P has already sent a message. So in order to type this, so the usual thing would be to have just the usual type, so send a message of type S and then proceed with the following. And since we have already sent something, we need to add a pause on top. And concerning the watch operation, so we just type the two branches, and then we record the fact that we have this alternative behavior in the type. We record this event here just to prove then subject reduction. So what do we guarantee? We have the usual guarantees of session types. Since we are based on the session types framework, we have the usual things that we prove in a session type. But then, what about progress? On one side, we have this bounded reactivity property. This is one part of the progress. But the point is that we could have live locks. So we have a process that is suspended because of a reception without the good send, and so we can go on instant through instance, just waiting for this send to appear. So what we prove for the typing point of view is that every input will be either matched in the current instant or in the next one. So again, it's a progress property, but adapted to our setting. And finally, you can play around with the setting, and you can add things that make the typing system quite complicated. But suppose that you need to have a scenario where you need that all the participants at each instance say, I'm alive, I'm alive, I'm alive, I'm alive, by sending something. Then we have also some machinery to prove this output persistence that forces the processes to send events at each instant. But it complicates quite a lot the typing system, so I won't present this now. So summing up, we have this reactive marriage with session types, and the interesting part is that we have these new two properties: the bounded reactivity, that is a semantic property, and the input timeliness, that is a typing property. And about open problems, so I didn't mention anything about delegation and branching, so we didn't go much into the delegation part, but we start thinking about the branching, and actually it seems that we can encode the branching with the watch construct. So it seems that we won't need the branching in our scenario. And then one can play around and say, okay, but what if we want to track events also in the typing system? Is it reasonable? Are there any properties that can match, there are significant in the setting of considering events inside of the typing system. So can we do something about this information or not? And what about pauses? So we did slice fix the slicing of time in the global type. Can we relax or not this hypothesis? There are a lot of questions that can arise from the typing system that we create. I didn't put a link on a technical report, but there is a technical report around, so just type multi-party reactive session and you will end up on the technical report. So thanks for your attention, and if you have questions.
Thank you, Cinzia. Any questions? Stephanie?
Hi, thanks for the talk.
All right, so thanks for the talk. First thing, technical report. Is that, I Googled it right now, but I found something from 2019. Is that the correct one?
Yes, is that the old version? Now we are working on a refined version where we don't have output persistence, so we clean up a bit.
Okay.
So it is the same thing. It is the same, at least the same syntactical thing, without output persistence.
Okay, so but that's the thing that I should look at.
Yeah.
Okay, then I have a question. I'm not sure whether I got the right intuition for logical instant. Maybe that's something that I should know, but I don't know. So what is meant by it?
So we don't have a clock that is timing the real duration of the instant. So the real duration of the instant is that we let all the participants evolve, doing their whatever they want to do, possibly 3,000 actions, and then when they all arrive to a suspension point, and the suspension is this explicit pause that is written in the code, this double send or this double reception or pending reception, when everybody has arrived to this situation, then we evolve to the next instant.
Okay. Yeah, I wasn't quite, I didn't get that, but now I understand. I thought whether it was tied to recursion, but it's really tied to this pause in the code. Is that correct?
No, but you just said it's really tied in the code.
Yes.
Yes, exactly. Yeah.
With a synchronization barrier for events.
Yes, right. Okay. Yeah. So I was thinking, like, I could also think in terms of a transaction, kind of.
Yeah. Yeah.
May
in some sense, yes.
May I ask another question?
Yeah.
How do I read the typing judgment? There was a slide with 2 typing rules, and you said, referred to the memory, and I wasn't sure which part it was. And then there's a subscript on the turnstile P, and I wasn't sure, does that denote a participant or?
Wait, because it's not responding as I want. Okay.
Yeah, this, exactly.
So here I'm typing a process. So this P means that I'm typing participant P.
Okay.
In this environment that just gives me information about the sort of the steps. And then I'm typing this configuration where I have the process and the memory.
So the comma M after the P comma, so the M union P, that's the memory, is that?
Yes.
Okay, good.
This is the memory.
Okay.
And this is the type.
Okay, thank you so much.
Thank you. Just out of curiosity, because you involve broadcast in your language, but there's a dual notion called, I think it's called gathering or collection, where broadcast is one-to-many, collection is many-to-one. And I'm just wondering, you would probably want a similar property if you have collection instead. How easy do you think it would be to adapt your setting to that operator?
So I didn't think about this, but I don't think there would be a problem, because the main problems come from recursion and pauses. So the communication for us is quite transparent. So I wouldn't say that that poses a problem, but then I mean you need to look into details, and when looking into details, problems can come up. But I think that we can have a similar treatment. But I don't know, because so something, it's not really, I really didn't think about this, but reading from many, so it means that you need to do some operation on the values, because you need to collect one value at the end. So it could be something that is handled by the semantics, I would say. So from the typing system, I would say that it should be quite transparent. It should be. I don't know if you have further comments.
I think it's philosophically different in the sense that I know that this broadcast and gathering mainly coming from parallel architecture, right? You have these parallel architectures in which you do this and that. But the broadcast here is mostly like a philosophical choice on the programming model that comes from synchronous reactive programming, right? That's the only way of contacting which you like to have different processes. So I do agree with Cinzia that there should be some way of accommodating that, but it looks like hard to fit. But I don't know if Ilaria would like to add something.
Yeah, actually, in our so maybe first thing I wanted to add for Stephanie is that the notion of logical instant actually comes, it's not an original notion we introduced, it comes from the family of synchronous languages that was developed in France since 40 years in the SPLASH' family. Actually, this synchronous reactive programming is a simplified form of SPLASH, where you have, I don't know, delayed reaction to the absence of an event. That's a bit technical. And concerning Hans' question, so in our broadcast, the threads, I mean the participants are not forced to read a message. They only read it if they need it. And in what you suggest, is the recipient obliged to receive messages from everyone or not?
No obligation.
No obligation. So I think that could be dealt with quite easily, yes? Yeah. Because, okay, maybe we can discuss it offline.
Well, there's also, take Matt's other question, final.
Yeah, but
Hi, thanks for the talk. So my question is, in one of the first slides, you showed the example with of the bidding.
Yes.
And I noticed you quantified the bidders with some subscript n. Yes. So I want to ask, is this n a known value? So when you write the protocol, you have to be aware of the full number of participants.
Yes.
Okay. And are you interested in looking to see how you can make a bidder or server agnostic of this? Because like, if we look at systems like eBay, like you said, you don't know how many people are bidding.
Indeed, I think this is an orthogonal problem. I think that there are families of session type where you don't know at the beginning the number of participants. So you have the, let's say, the global protocol, and then some of the participants join, and then when everybody has joined, then you start the protocol. But I would say that this is an orthogonal thing. So we didn't consider that setting here because we already had enough problems with the poses and the time. So we had to simplify as much as possible.
Okay. Thank you.
I would add, something. This is a well-known problem in synchronous, in these synchronous languages. They are not modular, actually.
Yeah.
Because to decide suspension, you have to know who are the threads.
Oh, right.
So,
that's also.
Be a trivial extension.
No, I don't think so.
Yeah, but when you set the protocol, then you have the network and the network is fixed.
Okay, if we had some mean of doing a poll to know who is there, then we know who to check at the end of the instance. But we have to know who are the participants.
Yeah, but it's clear that the tick reduction is a global property, so it's not compositional.
Okay, I think that takes us up to time, so thank you again, Cinzia. And it's break time, we're back at 4 o'clock.
Hmm?
You're able to get a personal top-level domain.
Oh yeah, of course, yes. Not easy, no? There are many competitors in the world.
I can imagine, yeah.
It's not easy, so but in the level of NL, I think it's right.
Yeah, maybe not so many entrepreneurs.
There are not so many, yeah.
Of course.
Yeah, it's another way of avoiding like local bureaucracies when it comes to websites and spaces in departmental structures of websites.
Okay, I think we're ready to start our last session of today. Before we proceed, I just need to give a word of gratitude to Simon for putting up with me in the organization of ST30. So thanks, Simon, for all your patience. And now our last session, thought-provoking talks, first with Jorge on the expressiveness of session types.
Thank you. So let me just first check whether this works. Okay, so not even with a delay. Let's see. Okay, so yeah, thank you very much for the introduction. So this is a talk about expressivity, and it's going to be actually kind of provoking talk in the sense of what expressiveness means, right? So it can mean many different things. And I will start with the traditional way of thinking of expressivity, right? So expressivity that has to do with process calculus, at least how people in process calculus understand expressivity. And hopefully I will be able to convey the message that actually it's something deeper, right? That there's something that goes beyond the traditional way of thinking about expressivity. So the first thing I wanted to start with was like a challenge. And it's actually a challenge that I try to articulate myself. So already some years ago, I did my postdoc on session types. I didn't know anything about session types. And I was just trying to understand all the different papers that were around, right? And then I was very surprised that there was no more comparison works about session types, right? Just for the sake of understanding ourselves, right? So I wrote these things. Of course, this is me citing myself, so this is self-promotion. Okay? This is 2016. So I was trying to articulate what it means actually from an objective point of view to have expressivity when it comes to session types. Right, so I wrote back then, I wrote like this. So we have all type system, which is the ground class in which session types are included. There are many different theories, right? The landscape is actually extremely rich. If you think about it, this is out of richness. So this is not a problem. The idea that there are many different things, actual richness, right? But the parameters are actually lacking, right? Expressiveness is the main motivation for proposing a new paper. You want to model this, certain prototype model, you want to model certain class of prototype model, current theories, right? Sometimes, most of the time, they are informal inclusions. That's why we want to have yet another theory, right? So my own proposal back then was to say, okay, well, let's try to use a formal way of comparison, right? So of comparing all these things, right? So the situation is essentially that we have lots of tools, some of them very sophisticated, but they are very different. Some very exactly how they are done, what is their scope, what we can do with them, what we cannot do with them, right? And unfortunately, if you think about it, for me, it's actually an ever-increasing challenge. If you take every component, yet another paper, yet another type system, with good reason, this is not meant as a criticism, right? But there is an ever-increasing challenge, right? And the interesting thing, at least if you think about this, is that at the end what you have is a different evolving class of correctness, right? So you have sophisticated type systems that ensure different properties, and usually these are the three properties that you would like to have, right? At least you would like to have protocol fidelity, you want communication safety, which at least in this context is quite related to this, and then you have level of freedom, which is the more difficult property, the most sophisticated one. Right, and then you have many different type systems, you have many different properties, many different ways of tackling different properties, right? So it's quite diverse, and it's actually quite a fascinating study, I will say. So what is the traditional way of looking into or thinking about expressiveness, right? So at least from the point of view of process calculus, you would like to think about the idea of relative expressiveness. You would like to compare different languages, right? By by encodability and separation results, right? So this is not particularly niche, so I think this is actually quite common in programming languages in general, right? So one way of thinking about connecting different type systems is by thinking about the classes of processes that they use, and then we can reason now on two levels. We reason in terms of the languages on which we apply session types or behavioral types in general, but we also think about encodings of the type structure, right? And this is the typical or the classical view of expressiveness, I will say, in terms of there is an encodability result. You can think of this as a correct compiler between two different languages. You could also try to think of separation result, which is a proof, like a counterexample, that a correct compiler does not exist, right? And my proposal is like, let's try to look at type languages with session types in particular from this perspective, right? And this has a number of advantages. So this is general. So this is rigorous also. You can prove theorems about encodability of separation results. This is flexible. You can think about the different criteria, correctness criteria that you would like for your translations, for your statements, right? It's flexible. It's also practical to some extent, right? Good. So this is let's say the point in which I would like to mention what this talk is about, right? So I will overview some of these recent results. It's not a complete exhaustive overview. It's kind of self-centered in the things that myself and my collaborators have done. And it has to do with expressivity of session types. And actually, we have done in the last 3-5 years, module COVID, we have done a number of different things. And all of them have a very strong expressivity motivation, right? So we have looked into higher order concurrencies, so the combination of the concurrency and functional features. We have looked into multi-party protocols, propositions as sessions, so the proposition as types apply to session types. We have done quite a lot of things connecting functional programming languages with types into type process calculi. We have also done what I would call property-driven comparisons, right? So we have different typing systems that ensure a certain property, for instance, double freedom or termination, and you compare the classes of processes that are used by those type systems. We have also more recently looked into co-algebraic characterizations of session type. This is a very strong, let's say, expressiveness argument there. Because of this result that we obtained in higher order concurrency, then we looked into reversibility, reversible concurrency. We have also looked into reactive and declarative models, and previous talk by Shinji actually is part of that. Most recently, with the most recent PhD students, we have looked into how to implement things and actually how to run specifications based on session types in a language called mod. So there are a number of different things. I won't talk about all of these things. I will focus on the first 3 items. Right. So and I have to say this won't be a technical talk. There is no space for me to go into all the technical details. I choose drawings, and usually for each drawing there's actually some technical story that I will be happy to discuss offline. Right. There is also, I put a note with pointers of the different things that we have done and the different things. It's not exhaustive. It's centered around the things that we have done. Of course, there are many things and many other people looking into similar things. Okay, so I will talk about 3 things. The first thing has to do with higher order concurrency. And it's my way of actually referring to things that we could call the traditional view of expressiveness, right? So we have encodings, we have language. We would like to know whether one language can be encoded, represented into other, up to some correctness criteria, right? In the specific class of higher order concurrency, what you have here is you have process calculi, in which some values may contain processes, right? This is one of the natural bridges between the lambda calculus and things like the pi calculus. And the key standard here, or the most famous language is the higher order pi calculus as developed, for instance, by San Giorgio. Right? So this is the kind of thing that the higher order concurrency brings in the session type setting, right? So this is a protocol. I won't argue this is the more realistic protocol, but it is a protocol that uses higher order concurrencies. We have one client, 2 hotels. And in order for the client to find out whether the hotels are reasonable options or not, this client sends a piece of code. Okay? I won't claim this is the more realistic thing, but this is a protocol. Right? And the idea is that the client sends 2 pieces of code. These pieces of code run locally on the hotel side. Right? And they ask and they query the hotels for the prices, and then the code themselves, they synchronize, and they take a decision. Okay? So this is a particular protocol. I think this goes back, who mentioned this earlier today, Dimitri's one of the Dimitri's theses, right? And this protocol it's actually indicative of the kind of things that you can do with higher concurrency and sessions, right? And if you think at least historically, what you can find is that this kind of settings, you can model them from two different paths, right? You can take higher order process calculi, in the sense of seniority, but many other things before that, and you add session communication, right? Another thing is, well, you will take your session pi calculus, and then you will add passing of abstraction. So this is another extension that you could consider, right? So there are different routes. This is probably one of the few technical slides. So I just wanted to show you some pi calculus with sessions, right? This is not fundamental for you to read every single element here. It's just a pi calculus with explicit session establishment, so you have different ways of thinking about shared and linear names. And then you have a set of values. You can communicate values, right? And in the case of the pi calculus, the values are going to be names, right? What we did, and this is referring to joint work with Nobuko and with Dimitris Koussapas. So what we did was to find an orthogonal way of adding this process passing capacity, which is actually passing of abstraction, right? So you will add an abstraction, which is a function from names to processes. So it's not the most powerful way of abstraction, but it's something that goes from names to processes. And that's how you will combine things at this level, right? So you will obtain a higher order pi calculus with sessions, right? And we call this Iso pi. Okay, we won't claim that that is the simplest acronym, right? So this has the kind of semantics that you could expect. So you have some beta reductions for the values, for the functional values. Again, these are abstractions from names to processes, right? You have the usual synchronization mechanism here, right? So you will have also types for this language. So you will have a category of, a layer of session types for this language, right? Of course, combining names and functions, then you will find those at the level of the type setting, right? So you will have value types. Some of these value types are going to be related to functional objects. Some of the other value types are going to be related to the names, right? Good. So the first kind of investigation that we did was actually trying to dissect this higher order pi calculus into simpler things, right? So we have this Iso pi, and we identified two sublanguages of it. One isolates higher order features, right? So it only has abstraction passing. There is no name passing. There is no recursion, right? On the other hand, you could also have another sublanguage which actually isolates the first order feature. So you have name passing. And this little drawing here indicates the fact that this is a sublanguage. This is the meaning of this arrow. And the first category of results, of the first sets of results that we obtained back then was actually the fact that we can encode this in this way. So there is an encoding in using functional elements of the first order elements and vice versa. So actually these two subcalculi are equally expressive. Right, and one of the interesting things here is that on encoding process passing or encoding abstraction passing into the first order setting, this is well known. This is what Sanyogi did. Right, the other direction, encoding name passing using functions, actually is crucially enabled by the presence of session types. Right, so we could do that because there were types around guiding the translation. Right, so we think that we were surprised by the expressivity that we realized back then, right? There was also a non-trivial use of non-contractive session types. There also for modeling certain things. So it was quite interesting. And there's some other things that appear in this diagram, like the extension of these languages, of this Iso pi with higher order abstractions, with polyadic communication, the combination of everything is encodable, right? So this is already a very nice language that has particularly cute sublanguages, and they are mutually encodable. And again, because I'm not going into the theories and so on, so every time that you see these arrows, you can expect like a formal theorem, preserving types, preserving operational correspondence. And one of the things that actually we discovered also here was the behavioral theory of everything. So in the book you were referring at the end of your talk about the need for type theories of bisimilarity. So we did quite a lot of things in that respect. So it's quite powerful framework, actually. So more recently, then my PhD students started to look into, okay, well, if we have this very nice and well-behaved setting here, sorry, is there something smaller? Is this really fundamental? Is there something that we can actually go further in this investigation? So one thing that he did was to say, okay, well, let's try to come up with something simpler than session types, right? We call it minimal session types, and minimal session types are simply types in which you don't have anything as a continuation, right? So you're removing essentially the thing that makes session types interesting, right? You may say, okay, well, you're ending up with a form of linear type. Yes, that's correct. Yes, but still, the fundamental issue here is that we are remaining in this nice framework in which we already understand a nice calculus H of pi, we already understand the subcalculi, we already have a lot of work done in terms of behavioral equivalences, type behavioral equivalences, characterizations, and so on. So we would like to remain in that framework, trying to see whether there is something even more fundamental. So, so this idea of minimal session types is just to replace these two things that we have here. We have no continuation, the only continuation possible is n. So you have these single shot channels. Some of the power of sequentiality is now translated or is now moved into the object that you have here. You need to pass more than one channel. So you have a polyadicity here. And actually this kind of idea came from, we revisited this very old result, I think a beautiful result by the way, by Joachim Power in 96, right? Back then people were concerned about expressivity, there were too many pi calculus, blah, blah, blah. So he came out with this result saying, well, every process can be decomposed as a collection of small chunks of parallel processes that can invoke each other. So you have these kind of collections of trios processes in which processes have at most 3 nested prefixes, right? So you can get something very small in terms of a pi calculus, right? One of the interesting things is that a process, a normal process, a source process, and its decomposition are very tightly related. So there is this very strong connection, a kind of full abstraction-like result between a process and its decomposition, right? So we borrow inspiration from that in order just to try to make sense out of these minimal session types. And the idea of a minimal session types actually can be explained more easily with a little drawing. So imagine that this is a process, right? This is a very simple process. You have a process inputting something. You are actually inputting one thing, an integer, then a string, and then you will output a Boolean, right? This is the corresponding type here. And what you will do is to decompose this process Qp into a process that actually is running 3 things at the same time. So this is a session, very simple session with 3 actions. So you will have in parallel 3 things interacting with each other, actually giving each other synchronization, right? So essentially, this is a process, a trio process that will essentially capture the first action. At the end of this action, you will need to forward the parameter that is received here. You will forward it to this other process that will do another input. You will collect that input, and then you will forward these 2 values to the last trio, right? Yes?
This is tuple.
Yeah.
And you know, there is a combinator can be decomposed.
Yes.
Tuple is a very powerful, another big means, and I knew Paro used this trick, but without the tuple,
Yeah,
probably you can.
So at some point we kept the polyadicity there for the sake of convenience, but indeed you can just go even, you can even decompose this into simple actions. Okay, I also forget I don't have this, so okay. So actually what we did then, so this is more recent results, so this is a PhD student who graduated last month. So actually what he came out with was he extended the hierarchy that I explained before, right? So we had, with Novak and Dimitri, we had developed this. Then he came out with this idea of a pi calculus with minimal session types. He showed that the composition, right, for both sublanguages, for the first order sublanguage of H of pi and for the higher order sublanguage of H of pi. So he came out with 2 different decompositions. And then he proved actually that the same kind of full abstraction-like result holds, right? So the idea is that, well, you will need to put your inductive machinery at work in order just to demonstrate that the previous intuitively schema that I had in my previous slide actually works, both for the first order setting and the higher order setting. And what I find, I mean, I think that this is quite interesting also in connection with other related work that decompose the session types into simpler things. But what I find particularly interesting is that these are session types explained in terms of themselves, right? So you don't need to go outside the world of session types to understand what session types are. So you can find a concrete reformulation or a concrete fragment of session types that will explain, that will allow at least just to model very precisely what is the behavior of a session type process, right? So this is the first thing I wanted to tell you. I don't know how am I doing in terms of time. I could talk forever about these kind of things.
Sorry,
yeah.
Quickly ask if there's recursion in these session types? Or?
Yes, there is recursion, and recursion at the level of types, and recursion at the level of processes as well. So, and the recursive case is particularly tricky and nice but yes, there is recursion here. So the other kind of result has to do with something that is with multi-party protocols, and has to do with what is expressiveness really? What is the purpose of doing expressivity beyond proving theorems, publishing papers, and so on, right? So one key purpose of expressiveness, I will say, is to transfer analysis techniques. So you do an encoding, you prove properties about an encoding with a purpose of like transferring some property to one language or to one framework to another, right? So this was discussed earlier this morning, right? So there is this idea of, we have a multi-party protocol, so you have three processes, P, Q, R are implementations of a multi-party protocol, right? And you would like them to interact according to some well-defined sequence of actions, right? What in 2016, I think, was that we proposed with Luis Caires a method of actually transferring the analysis of deadlock freedom from binary session types based on the Curry-Howard interpretation of session types to multi-party protocols, right? And the idea was to extract a process that we call a medium, right, that captures the sequentiality of the global type. So you take the global type, you extract the different sequential patterns there, then you connect that process with the different implementations, and then you will use that scheme in order to confirm the presence of deadlock freedom, right? And it was particularly nice because, of course, you're reusing the logical machinery. It's also nice because it handles delegation very naturally, which delegation is a pain usually when you're dealing with multi-party session types, right? Of course, a potential criticism is that this is a centralized approach, right? I understand the criticism. I don't fully adhere to it. I have my reasons that we can discuss on this, right? But then the question is, can you do better, right? So it's a valid question, right? Can you do better? Do you need also to apply to this? So more recently, my other PhD student came out with something simpler. Well, simple depending on how you see it, right? So you can actually intuitively dissolve the content of this process into the exact content that needs to be attached to each implementation, right? And the idea is that for each implementation or for each role in your protocol, you will come up with something called a router. So you will have a router for P, a router for Q, a router for R, and now these blends of routers and processes, they can communicate directly, right? And so this is sort of wrapper, right? And this is nice indeed because you're overcoming this centralized or fixed approach in which you really need to have something in the middle in order to communicate messages, right? And this is quite interesting because it works both for static verification. You have a type system that can allow you to type routers and implementations and so on, ensure deadlock freedom, right? But also for runtime verification. So the exact same machinery with minor tweaks can be adapted in order just to produce monitors that will supervise the fact that a certain multi-party protocol is implemented, right?
The lines between the nodes mean that they share exactly one channel, or?
Yeah. So let me tell you a bit about how this works, right? So, and again, this is a drawing, so we can go into the theory all you want, but I think the idea is it's good enough, right? So we start from a protocol, and here we mentioned a specific protocol which was a trigger for us, which is one of the protocols that Al-Chesty and Novoco mentioned in their paper, something that cannot be properly projectable for global and local types, right? So you have this protocol, then you have the implementation that is actually an implementation of each client with a router, right? So you have a router for the client running with implementation, implementation for the server running with its router, and so on, right? What is happening here internally is actually quite interesting because it requires a different way, a complete revisitation of the idea of local types. So we have something that we call relative types. There are types that talk about two things, two participants at the same time, right? And using those relative projections, right, we can synthesize automatically a router. And in the specific case of the static verification setting, you can use a type system, for instance, derived from the linear logic interpretation. This is a synchronous priority-based classical processes, right? And then you have asynchronous processes that enforce multi-party protocols in a deadlock freedom supporting delegation and recursion. So this is another way of actually thinking about expressiveness. The last thing I want to say, actually, is going beyond linear logic. And that's another way of thinking about what expressiveness means, right? Why are we tied to linear logic? There are very good reasons, right? But is there a world beyond linear logic? There is. So this is more recent work. I will skip the context. I just want to say, look, beyond the session type community, there is a lot of work in logics that have to do with with shared memory concurrency, right? And so one of the things that we did was to try to see what is beyond linear logic. So what we did was to consider the logic of bunch implications, or BI, right, which can be seen as the very core basis of concurrent separation logics, and try to recast these propositions as sessions, or the logic that corresponds to subsession types, from linear logic to BI, okay? This is a philosophical shift, right? So you're moving from the idea of consuming resources and using resources once or exactly once to the idea of accessing them. So this is like resource consumption and ownership. They are very different things. And in fact, linear logic and BI are known to be incomparable, right? And we think that this is interesting because this gives you a new angle to the idea of non-linear resources, right? So beyond replication, beyond clients and servers. Let me show you just the essential thing that you need to know about this. And is the fact that we need to go beyond the pi calculus in order to have something that looks like this. This is a new prefix that we call SPON. And this SPON prefix is an idea that encapsulates the structural rules that come from BI, right? So the idea is that this role is like new, right? It's an indicator that there is a list of sessions that should be contracted or discarded, right? So the whole idea of awakening and contraction is really encapsulated in the structure of a process, right? So you can have different examples of that. For instance, this is a prefix that tells you, look, I would like my context, some X that is in my context to duplicate the session X, right? Or I would like some session X that is in my context, I would like just to drop that session, right? And I can also have different kinds of sessions or lists mentioned here. Let me give you a more interesting example. So you would like to duplicate a session, right? So you have P here that is implementing something on X. You have Q that requires something on X, but actually requires its environment to duplicate X, right? So this is actually a sort of a request to the environment to say, look, I actually want to have 2 copies of P. One now mentioned in X1, the other mentioned in X2, and now you're actually duplicating these resources. So this is duplication. You could also discard resources, right? So you could also discard the fact that with the session in X should be killed, right? So you could also do that, right? And this very, in a way, this is a very elegant way of encapsulating the ideas of BI and the different structural principles that are the difference between BI and linear logic. I think my time is almost over. I just want to close by saying, well, I think the expressiveness studies are very interesting. They are necessary, they're relevant, they're challenging. And because of session types and the different forms of session types, they actually come out in different flavors and in different, actually subtle flavors, right? I have talked about 3 specific things, right? Higher order session concurrency, traditional encodability if you want. I have talked about this analysis of multi-party protocols using routers. And we would like to describe this in terms of analysis, transferring of analysis technique rather than a mere encodability result. The last thing I mentioned is something that appeared in Uppsala last year, is this idea of logic-based sessions based on the logic implications. And I would like to think that this is actually a nice step towards going beyond linear logic and try to connect with other kinds of formalisms. And I think this is where I will stop. Thank you very much.
this is probably two questions in one. The first one has to do with higher order processes. Maybe it's just me, but I thought I know that the result that higher order process calculus and the pi calculus are equi-expressive. That goes back to the work by Ben Thompson on his work on chocks. What was it exactly that was gained by session types? That's the first question. Second is the use of minimal session types in this setting. Isn't that very reminiscent of the Kobayashi and others' work on encoding session types as linear types?
Right. So thanks for the question. So as for the first question, that direction, encoding higher order into first order, I mean, you gain type information, but yeah, you just follow the usual idea in order to communicate a process, you communicate a reference to that process. That part is unchanged. It's the other direction in which you really benefit from knowing from session types, how to encode name passing using processes. Regarding the idea of minimal session types, yes. So the main difference is that we're explaining session types in terms of session types. The Kobayashi result is explaining session types in terms of linear types. You will say, okay, well, they're not really that different, right? But my claim is actually, what can you prove about this, right? Because we are remaining in the world of session types, we can reuse all this machinery in terms of behavior equivalences, and we can prove something like this, right? Because this is a session type process, this is a session type process, this is a behavioral equivalence defined on session type processes. I think that's the main distinction point. Yes?
The equations you have below, you say it's a type setting, but it's are you translating the session types from one side to the other, or what?
No, because everything.
It's not the same session type, right? Because in one language is the full one, the other one is the minimal one, right?
Yeah, but
so do you have encodings also?
No, because essentially, what you have, you said precisely, right? In one hand, you have like the full session type. In other hand, you have one session type that happens to be short, right? So at the level of behavior equivalences, you track the fact that some things are, you have one session type and then you have a list of session types or minimal session types. But this is not really.
But you lose causality when you short.
No. No, we don't know. Precisely because of the way these things are done. Here, so the causality, and this is a very important point, the causality is transferred from the session type to the construction of the processes, right? So it's embedded there, you don't lose it.
I think that for the sake of time, we'll just finish here so that we don't run out of time. So let's think.
Thank you.
Yes, thank you. Trying. We're still trying. Oops. What am I doing? Is this coming? Yeah. But I need to. Yeah. Right. Very good. Right, but I think I need to try and mirror the. Perfect. Right, okay, so Vaško and I have been writing a book on session types for some time. So the title is What We Have Learned, but I mean, I've prepared the slides, so it's sort of my view on it. It may be that Vaško would have a different view. You'd have to ask him. I did send him the slides at lunchtime, and he said he thought they were good, so let's see. Now, I should say this is not exactly the first book about session types, because there's Ornella's thesis, which was published as a book and is mostly about session types. But I think this is the first, setting out to write a book which is an introduction to session types. So in the beginning, which I don't exactly remember when it was, but I think we were in London at an event, let's write a book about session types. Yes, good idea. And this was in either 2014 or 2015, so quite a long time ago. And then nothing happened. So in the summer of 2019, we again said, let's write a book about session types. Yes, good idea. And at that point, we actually took the next step and submitted a proposal to Cambridge University Press. The proposal was reviewed, accepted. We had a contract. Some deadlines were suggested. And so we got started. So in the autumn and through to the beginning of 2019, 2020, I had a few visits to Lisbon, and we got started. 1st of March 2020, Vasco arrived in Glasgow to spend part of his sabbatical on a 3-month visit in Glasgow. And you know what happened next. So 18th of March 2020, Vasco went back to Lisbon. And I'm sure we've all got similar stories. So, I mean, Luca Padovani was also supposed to visit Glasgow for several months that year, and he never even got as far as arriving, and so on and so on. So we carried on in remote mode. And we've been collaborating for a long time with a lot of remote working, so that was not too bad. So we thought, well, how hard can it be to write this book? We know what we want to include. We've got a lot of source material, so there's this paper by Vasco, Fundamentals of Session Types, which is a nice presentation of all the basics. We wanted to include subtyping, so there's my paper with Malcolm Hole about subtyping. We wanted to include functional programming, so Vasco and I wrote a paper some years ago about functional programming with session types. And I now realise when putting these slides together that the title of this paper doesn't say anything about functional programming, although it's published in the Journal of Functional Programming, so maybe that's enough to say that it's about functional programming. We wanted to include something about the encoding by Nava, Giacchino and Sangiorgi about, this is what was referred to in Jorge's talk actually, encoding session types into linear types. We wanted to include something about the developments of the propositions as types connection, the work by Luis Caires, Frank Fenning, and afterwards by Phil Wadler. And we decided at an early stage that we were not going to include multi-party session types because just dealing with the main topics in binary session types is plenty. It certainly would be a good idea for someone to write a book about multi-party session types, but I don't think it's going to be me and Vasco. So how hard can it be? Well, so of course you have to work out how to present everything step by step in a consistent way. We wanted to give a good account of the sort of the theory of the co-inductive approach to dealing with infinite session types. You can find a lot of papers that say, well, we'll interpret these rules co-inductively, but to find a thorough explanation of what that really means, we wanted to do that. How to deal with infinite process behavior, so replication or recursive definitions or whatever. How to deal with the, so at the core of session types, you've got linear types without sharing, but then you want to add nonlinear types with sharing. There are different ways of presenting this. Sometimes your type environment has two regions, some of which are shareable and some of which are not, or you can have explicit contraction and weakening rules as you would see in a logical system. I said we wanted to include the propositions as sessions material, the linear logic correspondence, but there are these two rather different presentations of that, the original one by Caires and Fenning and then the later one by Wadler, so that there was a decision to be made there. And I said that some deadlines were suggested. So we originally suggested a very optimistic deadline. And I can't remember exactly what it was. It might have been sometime towards the end of 2020. And at some point we realized we weren't going to make that deadline. So I contacted our editor at CUP and said, look, I think it's going to take a bit longer. And the way he responded, it sounded as if he was surprised that we were taking the deadline seriously at all. I mean, you know, he was quite surprised that we were bothering to inform him that we might not satisfy the deadline. Anyway, so we got to work and we started simple. So we start with a very, very simple system, no recursive types, no recursive process behavior. Everything we do throughout uses this double binder style, so separate names for the two endpoints of a channel, and new binds both of them. You can find different treatments of the end session type in the literature. Sometimes there's just one end type, sometimes it's separated into two dual types. Sometimes end is a shareable type, sometimes it isn't. And we started off with no copying or sharing at all, so it's purely linear. So it's quite a basic system. Something we discussed quite a lot is that we don't have any primitive data types, so it's just session types. And then we encode Boolean types using branching and selection, and then use some examples based on Booleans. And you know, the plus point about this is that it keeps the language as simple as possible, because if you start introducing primitive data types, if you say you want to have integers or whatever in your examples, I mean, either you have to actually properly develop the typing rules and theory for that, or you have to be informal and say, well, we could easily add primitive data types and then we'll use them in this example. But then if we say we could easily do X without actually showing how to do it, then the book isn't fulfilling its need to provide a foundation. So this is what we ended up doing. And the main drawback from my point of view is that there are an awful lot of examples where you're passing around channels of type end just because you want to have some kind of piece of data to pass around. Anyway, that's what we did. And then we prove type preservation and type safety. And the structure of the first chapters is that we start with this simple approach and then we gradually extend the language and sort of go through a similar development, showing what's different. So one thing, of course, we've heard already today, another key property of session type systems is session fidelity, which is that the sequence of messages that's actually exchanged at runtime matches the specification expressed in the type. And a lot of multi-party session type papers prove session fidelity, but we didn't manage to find a paper that proves session fidelity for a binary session type system. If anyone knows one, please let us know, because it would be good to have a citation. And there's actually, as you know, if you've tried it in the multi-party setting, it's you need some extra machinery to prove session fidelity. So I think in the end, this has turned into a rather complicated exercise for the readers. But it would be nice to have a citation for where someone else has done it. So then we move on to infinite behavior. As I said, we start off by infinite type as actual infinite objects with infinite derivations. We try to explain the foundations for this. This paper by Dexter Cozen and Alexandra Silva, Practical Co-induction, is a very good reference for doing things co-inductively. Then we move on to do the usual kind of finite syntax using a rec construct. We thought about trying to take the same approach with infinite process behavior, and it seemed to get a bit complicated because of dealing with variable binding in a thorough way. We're not quite sure how to handle an actual infinite typing derivation for an infinite process where you've got an infinite sequence of bound variables. So we just went straight to a finite syntax using systems of mutually recursive equations defining process behavior. Something else that came up this morning in Peter's talk was this point about having to be very careful with the definition of duality of session types if you have recursive types that are not tail recursive, so if you allow recursion in the message position. And so we've included an explanation of how that works based on the approach of Bernardi and Hennessy. So then we move on to nonlinear types and sharing. And the key thing here is that if you've got session types which are stateless, so as for example here a recursive type where after sending the first message you go back to the original type, then these types can be safely, channels of these types can be safely shared. You don't get race conditions due to the statefulness. Now some presentations of session types start off with pre-types, and then you add a qualifier which is either lin for linear or un for unrestricted. So unrestricted means shareable, and then you have to be a bit careful that if you're constructing a type and declaring it to be un, you have to make sure that the structure of the type was actually safe to be declared as un. So in the end, we've got a different approach, which is that instead of lin and un being qualifiers that you attach syntactically to types, they're predicates that a type can satisfy. So the types that satisfy the un predicate are exactly the ones that have this stateless character. And the types that don't satisfy the un predicate satisfy the lin predicate, so they're negations of each other. And one thing this supports, which actually was already in Vaško's paper on fundamentals of session types, is that it's possible to have a type which starts out as linear and then evolves to become something shareable. So you can have a channel which initially must have only one owner to avoid race conditions, and then after some initial sequence of communications that the channel can be shared. So this is a little example here. An initial input of a Boolean and then going into a stateless type that repeatedly inputs ints. And there you see I've violated the principle of not having any primitive data types, but you see how attractive it is to be able to just throw in bool and int when you're trying to explain something. So the way we deal with the shareable types is that we have explicit rules for weakening and contraction. So this is contraction. So contraction means replacing two names y and z by a single name x and doing the substitution. And you can only do this if the type t is unlimited or shareable. We had quite some discussion about the concept of sending a channel on itself, so where the message is the same as the channel. And it's possible to construct examples of processes that do this. They often seem a little bit artificial. Now, the thing is that once you've committed to having an explicit contraction rule like this, then you can automatically type processes like this. There's no choice about it. So you're stuck with them in the situation where the type is unrestricted. So then there's a separate discussion you can have about whether it's possible to do send x on x when the type of the channel is linear. And it is possible to make sense of that if you decide to insert a typing rule for it, and then the difficulty is in terms of writing the book, when you've got design decisions like that, and okay, you set them both out, and then what do you do in all the subsequent chapters? Do you maintain this, these two options and so on? So this is one of the ways in which things get complicated.
What is your decision? You include it or this XX?
So it goes. We include it for a while and then stop. So the next chapter. so after the sharing chapter, the next chapter is about subtyping, and we still have this send on self possibility, and then eventually we get to a chapter about type checking algorithms, and then we just drop the linear one because it's a bit complicated. But you still have to, for the shareable types, you still have to allow x send x because it's there. So we have a chapter on subtyping. This was one of the chapters that really didn't have a lot of problems. We did manage to closely follow my paper on subtyping. We did make a small discovery. I'm not sure whether this is original or not, but I don't think I had seen it before. So a lot a lot of work that has linear types and also subtyping. Just, from the point of view of subtyping, the linear world and the non-linear world are just completely separate. So if you've got a subtyping relationship, either the types are both linear or they're both non-linear. Now actually, in the paper that Vashko and I wrote about functional programming with session types, we have a subtyping relationship between linear and non-linear function types, which is quite convenient in some ways, and that's safe. But still, the linear and non-linear session types were separate. But once you've got this idea of lin and un just as predicates that a type may satisfy rather than decisions or rather than syntax, it turns out, the subtyping relation is also defined on the structure. So it turns out to be possible to have a subtyping relationship between session types where one of them is linear and one is non-linear. So here's an example. So this is an example using an internal choice type. So we've just got one option, which is A, and then the continuation is the same as the original type. So this is stateless, it's shareable, it satisfies the predicate. This one starts off with a choice with two options and then goes into that one. So this has to be linear because you've got this first step which is not stateless. But according to the definition of subtyping, L is a subtype of U, so you get this mixing between the worlds. And this looked a bit, when we noticed this, we thought this was a terrible mistake and something must be badly wrong and we'd be back to the beginning for this chapter and so on. But it turns out that it's perfectly safe. You would worry intuitively that you might have a channel which is supposed to be uniquely owned because its type is linear, and then you use subtyping to promote it into a situation where it's not uniquely owned anymore, it's shared, and surely something could go wrong. But actually what happens is, if we take something of type L, promote it to type U and put it in a context where it's being used with type U, well, the context in which it's being used can only be using it in a stateless way, because that's what the type U says. And so you don't get the opportunity to take advantage of the stateful nature of L, and so nothing can ever go wrong. So the promotion in this case, usually going up the subtyping relation, you're discarding some information, you're forgetting something, and what you're forgetting here is that the L type had this stateful character. So everything's fine, but that was quite an interesting observation. So we are, I'm afraid, still working on a chapter about algorithmic type checking, attempting to follow the approach taken by David Walker in his chapter on substructural type systems in advanced topics on types and programming languages. And what we're doing is, all the type systems in the book, of course, are presented by a collection of inference rules, and so the type checking algorithm is also presented as a collection of inference rules. This is quite common in the literature. It makes everything look consistent with the way that we present the declarative type systems. But you could argue that if you want to present an algorithm, doing it by a collection of inference rules is actually quite strange. And if you look at papers that are actually about algorithms and see their presentation of an algorithm, what you definitely won't see is a collection of inference rules. You'll see some pseudocode that you can actually see how it maps into code. So this then leads into questions about how should we present these rules? Should they be as clear as possible? Should they be as compact as possible? Should they make the proof as easy as possible? Should these rules make it easy to see how to do the implementation? And this has led to a lot of discussion. Functional programming, thankfully, this chapter did proceed without any difficulties, and we managed to base it on our previous work, so that's all okay. Encoding session types in linear types. So this is the work by Ornella and the others. We did something which you might say is cheating a little bit, possibly, but one of the things that this encoding has to deal with is that the source language is this double binder form of session pi calculus, and the target language is pi calculus with a linear type system, but not with the double binders, so just a single mu x. And this leads to a certain amount of extra, bureaucracy and bookkeeping in the definitions and proofs and so on. So we decided to simplify our lives a little bit by converting the linear pi calculus, the target language, also into a double binder language, which is then consistent with everything previously in the book. We did a little bit of experimenting about exactly how to define this encoding. So, the original work, this encoding is defined on untyped processes, and some later work defines it on typing judgments. And it's a question of how you make the proofs go through. So we've ended up with a small variation where what we're translating is untyped session pi processes, but they do have type annotations on their restrictions, and we have optional type annotations on the restrictions in the target language, and this enables us to define the encoding without having to assume a typing context, but all the proofs seem to work quite well. And then the final chapter is about the linear logic connections and the propositions as types approach. We discussed this quite a lot. In the end, we decided to follow Wadler's approach, the CP approach, rather than the original approach by Frank and Louis using the dual intuitionistic linear logic. I will say that we now have a much better understanding of the differences between these two presentations. And I think one aspect of this is that the DIL approach matches the normal pi calculus treatment of replication quite well, in the sense of sort of pulling out one copy when you need it from a replication, whereas the Wadler CP approach, you sort of duplicate an entire replicable process and then convert one of them into a single form that you want. However, we felt that the Wadler CP approach matched quite well the general style of typing rules that we had earlier in the book, including the explicit contraction and weakening rules. So we decided to go with that. So the title of this slide is duality, which is, of course, essential in session types, but on this slide it's not what you think. So this is going a little bit off track, but when I was much younger, growing up as a child, I remember that my sister had a big poster which illustrated lots of common sayings and proverbs, and a lot of them were in kind of dual or complementary pairs, which was quite an entertaining way to present them. So one of these is, many hands make light work, or there's the more intellectual version, which is that two heads are better than one. But the dual of that is that too many cooks spoil the broth. And of course, we know about that in the context of software engineering. So I don't think we've spoiled the broth or the book. I don't think two cooks is too many. I think it's a helpful number. I think we've worked very well together. Another well-known saying is that a problem shared is a problem halved. I think this is perhaps more often applied to emotional problems rather than technical problems. But my variation on this is that a problem shared is a problem with two solutions that then have to be discussed and compared at length. But I think normally you end up with something better because it's been compared and discussed. So we do think we've nearly finished. Thank you to everyone who is going to read chapters and give us feedback. You don't know who you are yet. If you're thinking maybe they'll ask me to read a chapter, yes, we will. Hopefully quite soon. we hope the book will be a useful introduction to binary session types and a reference. You know, working together has been more fun than trying to write a book solo. It's certainly going to be a better book than it would have been if I had tried to write one myself. You'd have to ask Vaško whether he thinks the same. Someone should write a book about multi-party session types. I also think it would be very interesting to have a book that took the propositions as types approach right from the beginning and did everything in that style. It would be, I don't know if any of the obvious people have thought about that, but it would be a good thing to do. So that's it. Thank you for indulging me by listening to a talk about what Vaško and I have been working on, and we hope you'll hear more about the availability of the book before too much longer.
Not a question, but the comment is that X send X, this you can encode the untyped lambda calculus. It's like lambda x dot xx and lambda x dot xx. So you can encode, if you can send channel to channel, you can encode untyped lambda calculus. That is one example, but I thought your subtyping algorithm doesn't have any problem to send channel to send, I think. But it may be shared channel. I don't know.
I don't think it's a problem. I mean, you need a suitable recursive type for the channel,
yes.
and then I think everything is fine. Yeah.
But you can, that is also useful for encoding.
Right. Yes, I see what you mean. Yes.
Another question at the back.
So a technical question and a challenge. So you... Is it on? Yeah. So why did you decide for the double binder instead of the polarities? So is there a technical reason for that that makes life easier?
So I think the concept is very similar, that you distinguish carefully between the two endpoints of a channel. I think using the double binder is a bit simpler technically, because otherwise you get into questions like, okay, you've got x, you've got x plus, you've got x minus. So what is the exact relationship between x and x plus, if any? And you end up substituting. When you've got a bound variable on an input, say you write it without a polarity, and then you're substituting a polarized variable for an unpolarized variable, and it's all. I think now everything is simpler if you just use plain names with a double binder, rather than the plus and minus.
Are you going to start volume 2? Type behavioral equivalencies, for instance.
Well, it's possible that we would not be the best person to write that one either. Yeah, we're
Mine is a quick question. Do all proofs come mechanized?
No. In fact, you said, do they all come mechanized? Well, it's even worse than that. None of them are.
So a very quick question. What is the intended audience of the book, right? So is it us? Is it people outside? Is it undergraduates who are very motivated?
That's a good question. So your new PhD students, or maybe master students if people are teaching courses at that level, or maybe other researchers from outside the field who want to find out more about it.
Okay.
That's the hope. How many of these people there are in the world, I don't know.
Thanks, Simon, again.
Thank you.
Okay, so this is my report on what would have happened if I had written that book. That was the last line in Simon's talk, right? Where you start from the beginning with propositions as types, because that's where I actually started. So it's not a stretch, because I came to session types late in my life, okay? And I started with understanding them through the lens of propositions as session types. Okay, so this is somewhat impressionistic, I guess. For this kind of audience, this is okay. And I don't have any references because I started and then it was snowballing. I said, either I give up or I spend another couple of days. So I gave up, okay. So if you're not cited, you're not alone. I don't even cite myself, okay. Okay, so what is really not different, right? That's, because you want to understand the difference, you also understand the similarities. So in the ordinary logic, we have ordinary types, going back to work in the 60s, we have the distinction between the data type and the phrase type. And in session types, we have the type of a message and the behavioral type of a process, and those are really the same thing. So, I mean, a function type is a behavioral type because you're not saying how the function is represented. You're saying, if I give it an argument of this type, it gives me a result of that type. So that really doesn't distinguish session types in any interesting way. So normally you would say that intuitionistic propositions are related to simple types since 1969, we know that. But here we know, well, linear propositions are session types. So again, it's not really distinguishing characteristics of session types that you can relate it to logic. And then in ordinary types, we prove preservation and progress. Well, we have the properties like session fidelity and deadlock freedom, so it's also not really distinguishing session types from other things. So where do things become different, okay? So the first most important, well, very big difference is that right from early on, there was a distinction between the global and local types, okay? So coming from the functional world, or even the imperative world, if you will, there is no, as far as I can tell, corresponding a bifurcation of types. So I'm actually not 100% sure that a global type should actually be called a global type, or whether it's something else entirely. I'll come back to that towards the end of my talk, okay? So I don't like the word binary session types because they aren't binary, okay? You can have multiple clients to a server. You can multicast a message. So it's not really that every channel has two endpoints, even though it started that way, but it doesn't really extend that way. I really like to think of those in terms of global types and local types. And then another thing makes it that it's right from the beginning substructural, and maybe now we're more used to dealing with that because we have languages like Rust. We do quantum computing, which is by nature substructural. So the point that the type reflects some aspect of the process state, and then the thing that is surprising to most people who come from the other world is that the channel types evolve during communication. So in a functional language or imperative language, if X is a variable of type int, it's always going to be a variable of type int. If you have a function from int to int, it's always going to be a function from int to int. It doesn't change as you compute. But with channel types, they evolve. And that was the hardest thing to wrap my head around when I started on that. So I'm going to just focus on two, partly because I don't really understand one. Okay. And I do want to talk about the end about what we have learned more broadly. So I think that at the beginning of session types, there was a very wide gap between session types and what people were doing in functional languages and imperative languages. I think by now the gap has narrowed because people like me have cannibalized session types and taken some of the idea and applied it to functional languages and other contexts, and that diminishes the difference between the two threads. which doesn't, of course, diminish the impact that the session types had. Okay, so I'm going to use a very simple example, and I'm going to use in the propositions as session notation. So a store, or as you could think of it as a network also, if you do true sharing, it's an external choice, so the client can do two things. They can either insert an element of type A, which is going to be a channel into the store, or they can delete something from the store, to which the provider, the server responds either, oh, there's nothing in there, and then we'll terminate, or there's something in there, then you get the channel of type A, and it behaves again like a store. So the way we type processes is this way. We have a linear context delta, we have a process P, and we have a channel X that is provided by P, and P is the client to all the channels in delta. So I prefer the intuitionistic approach instead of a classic approach because it is more easily related to functional programming. And if you want to integrate the two, it's nice to have that similarity actually to work from. Okay. So what is the correspondence here? Well, I'm just talking, just to explain these types, probably most of you know this thing. External choice, the provider here receives a choice and then continues at type A or B. Implication means the provider receives a channel of type A and continues as B. If it's an internal choice, the provider has to send either go to the left or to the right and then continue with A or B. A tensor B, the provider has to send a channel A of type A and behave like B. And at 1, the provider sends a unit element and says, now we're closing the channel. Okay. So there's no explicit duality here the way there are in many other session type formulations because we have this distinction between the provider and the client, which is embodied in this typing judgment. Okay. And so this, one of the reasons I like this example because it's very close to what Stephanie and I had showed as the universal session types for asynchronous communication, but also it uses all the connectives pretty much that we have. So, okay. So here's a small program that shows type evolution. I only wanted to show it because, like I said at the beginning, it seemed very strange. But so we have a server which provides a store along channel S. So I like kind of not the PyCalculus syntax anymore, but programming language syntax because you have to write programs. I write these programs all the time. I'm giving a course right now on substructural logics, and I had students implement all kinds of programs. And so they actually have to type them in and run them and try them out, and I have an autograder for all of that. So, so you receive along S either an insert or a delete label. Okay. So at this point, the type of the channel S is now something that accepts a channel of type A and behaves like a store. And then you have to receive along S some X, which has type A, and after that, S is back to the type of a store. So the only way that I can write these programs, unless you have a lot of experience, is you have to yourself, when you write it, you have to track the types of the channels. It's very strong type-directed programming, much stronger than in functional programming, right? Because the typer gives you a very strong hint about what you have to do at each step in the program. When you delete, then this is the type of the channel. So that's an internal choice. Now we, as a provider, as a server, you have to send, okay, in this case we send, oh, we have something. At this point, channel S says type A cross store A. Now we have to send an element, say Y, wherever it might come from, and then S cycles back to be of type store of A. Okay, so we have this evolution of types, and like I said, this is a distinguishing characteristic of session types that was very different from what people sort of in other domains looked at in terms of types. Okay, so even today in languages like Go, which were not designed that long ago, channels have a fixed type. Okay, so you can't write this kind of program. What you have to do is you have to take like the union of all the possible things that might be sent across the channel, and that's the type of the channel. So you don't have very much information. On the other hand, there's a Ferrite session type library for Rust, which encodes some of this state change, which you don't get in languages like Go. Okay, so here's the sample rule for a typing rule. I'm only showing it because I'll have a little bit of that later. But when you receive along X, any of these labels from the label set L, which is some kind of finite set, then we have to check all the branches, okay? And so since we're providing channel X, we check all of them against X. But that means that we have to do the same thing on the left-hand side because the provider and the client have to continue to agree on the channel they communicate on. So here, if the client has an external a choice between all these different labels, they can pick a label K, send that, and continue with Q. And now the channel X has evolved to be of type A of K. Okay, so to prove preservation in progress seems at first impossible because, well, the channels change type. How are they being preserved? But what saves you here is that if you look at the dynamics which we specify, this kind of multi-set rewriting style, so you have a receive along channel C and a send of a label K along that same channel, then we pick out branch piece of K, and here we continue as Q. And the way you prove preservation, well, first of all, the type evolves here from this external choice type to A sub K. And then the important part is that server and client agree on the type change. And then the final thing to observe is that C is a private channel between the two processes. So it's an internal action, so the type change is not externally visible at the external interface of the configuration. And that's how you get preservation. And then progress at deadlock freedom also holds and is, I think, much easier to see and to talk about than in the classical setting, actually, because of the way cut is written, we have a natural partial ordering we could induction over. Okay. So, but you have to ask yourself if we backed ourselves into a corner, because a lot of communication is not synchronous the way it's here. So a lot of computation is not linear, it just reuses data. A lot of communication is not dyadic, so it's a multicast, for example, so it's not just two processes. So fortunately, because it's actually based on very sound principles, we can extend this idea of local session types and continue to generalize it in order to sort of accommodate extension past these limitations. Okay. And I'm going to walk you through these because this is part of where the story between regular types and session types start to come a little bit closer to each other. Okay. So the first thing we have to say for asynchronous communication, that messages are processes. And then if you have two consecutive messages on the same channel that are asynchronously sent, one can overtake the other. So you cannot just have a channel change its type when a message is being sent. So if you want to have type safety, you need a continuation channel. Okay. So what happens here is something like this. So if you have this kind of, now I dualize things to put on the other side, you have an internal choice, so the provider is going to send you a label and you branch on what that is. So then previously we just say, okay, X becomes now A sub L, and we have to check that in each branch. And here you receive not only the label L, but also continuation channel X prime. And then X prime is of type A sub L. Okay. And once you do that, the tricky part is what are the messages? Well, the messages look like this. So you send on the channel X, which is this external choice here, not only the label K, but also a continuation channel X prime. And this has to become, logically speaking, an axiom. It says something like A entails A or B. And so because it can't have a premise, because a message doesn't have, as such, a continuation. It does have a continuation channel, but not a continuation process. So we have to type this thing with these kind of axioms. But we can do that. And then the dynamics is actually simplified because we have a process sends along channel C, a label and a continuation channel. This one expects one of these labels and a continuation channel X prime. And then it becomes this process Q now depending on C prime. So we can still track the provenance of a channel, so this is still implementable by using like the ordinary notion of a channel, even though it doesn't look like sort of in this abstract theory anymore. And it turns out that ultimately this notion of provenance of a channel, when you translate to the functional world, is related to some idea of data layout. Okay. Okay, so now what does the program look like now? Well, it looks a little different because it has more syntax. But when you receive along S an insert request, you get a continuation channel. Then you receive along S prime, an element of type A, and a continuation channel S double prime, which is a store. And then you can recurse with this new S double prime here and become a server again. And similarly here, when you send along S prime a sum, you have to give it a continuation channel, and then you have to use that for further communication. So you have to write more syntax than you normally would, but it's still analogous. Okay. So now the second step would be, now that we have asynchronous communication, multicast makes sense. We can send a message to multiple clients. Okay. So for doing that, we have to distinguish between the linear channels, which have a single client, and shared channels, or nonlinear channels, which possibly have multiple clients. And so in the semantics, the green processes here, they're just as linear as before, and these purple processes are messages that are persistent, and persistent in the sense that multiple receivers can receive that without consuming it from the wire. Okay? And so this raises the issue that you have to garbage collect these things, but that's kind of a separable issue. And so then you can multicast, and here is the rule for doing, this was a previous rule. So to lend along a shared channel, you become a persistent message along the same channel with the same contents. And a persistent message can be received. Multi-set rewriting, this bang is kind of derived from linear logic. It means that this thing here is persistent. So even though it's received by this process, it can still be received by other processes. So in this framework, it's very easy to model things like multicast. Now I'm going to skip over the next part, because we can also do shared services, but I want to move on to talk about other things. So let me, this is a little bit less surprising. Okay, so then you come to the point where you want to combine the linear and the nonlinear types. Because, well, part of your program, you'd like to have messages being linear, being consumed. You don't want to have to garbage collect your distributed system, which is a very hard problem. But sometimes things are just not linear, and so you'd like to have both. And the way you can do that is you can have two layers, a nonlinear and a linear layer, and you can populate it with the usual constructs from each layer that you like. And then you just need to go back and forth and investigate what are the properties of these shifts. You can figure out what these laws are, but basically they form some kind of adjunction. There's really not a lot of variability. Your hand is kind of forced in this. So the mode signifies whether a channel, for example, if you use this for channel communication, would be dyadic or variadic. So if it's two endpoints or one provider with many clients. So the mode just determines essentially at this point whether you have garbage collection or not, okay? Whether it's linear or nonlinear. This difference is significant, so I don't want to downplay it, but unifying it this way is actually a very nice simplification overall. So when we did the original work on propositions as type, we used bang, and bang is much less pliable. You can do a lot less with that than you can do by using these shifts. Okay, so where are we now? Okay, so taking stock. So we started with synchronous linear session types, and the channel types evolves during communication. So now, at this point, we have asynchronous session types, where the continuation process is replaced by continuation channel. And so now we have combined linear and nonlinear types. Types no longer evolve because we have the continuation channel, but we can track the provenance, so it's still implementable in a reasonable way. So now, the rest of the talk I want to spend on what's the connection to what you might call ordinary types. Okay. So in order to give that connection, I need to briefly talk about process composition. So the process composition here is not just has a single channel that's being bound, because in the intuitionistic setting, it's nice to have a single channel that the provider and the client agree on rather than have two. But it's not a big difference. And then the dynamics of this process composition is that if you have a process that has this kind of spawn operation, then it bifurcates into two processes, one executing the provider P, which provides A, and the second one being the client Q, which uses A, and A has to be a fresh channel for this to work correctly. And from the secant calculus, if you happen to know this kind of thing, this is just a cut. So the shared channels get replicated on both sides, and the linear context and linear channels get split, and then you get a good typing rule for that. Okay, so at this point, really, session types become almost ordinary. because we can compile functional expressions with a destination D, which is similar to Milner's thing. It was referenced earlier as well. And with Luis and Bernardo, we also looked at something similar. So if you have a functional expression of type A sub m, where m is the mode, could be linear or shared, then you can compile it in this way. And now this process here has a destination. So expression E just returns a value, but here you can't just do that. You have to communicate along some channel D. So what does it look like? You have this composition of translation that E1 applied to E2 with destination D. Well, you have to run a process E1 with destination X1. Then you have to run a process E2 with destination X2. And then you have to send X2 to X1, because X2 is the argument and X1 is the function, right? But that's not quite enough. You also have to send it the continuation channel for the result of that application. So you have to send it to D as well. So you send, when you have a function application, you always give it one more argument than you think you need, because you have to give it a destination. And then a functional lambda expression is compiled like this. We receive along channel D, so it immediately blocks and waits to receive. What do we receive? Well, a value, the argument x, and then a new destination D prime for the result, and then we evaluate the body with this new destination that we've just received. And when we see a variable, we're supposed to compile it just then we forward, which is the identity rule of the sequent calculus, from x to D. Okay, so because we have this composition of translation, at this point it's very easy to interpret what functional programming should mean. We just have to play with the scheduler. Okay, so for example, if we schedule always this until it communicates along X1, we schedule this until it communicates along X2, and then do this, we get kind of a call by value interpretation, and so on. And here's a simple example. Lambda XX applied to D just receives along D the X and a D prime, and then forwards X to D prime. So it's what you would expect the process to do. Okay. So the parallelism is possible, but you can get called by need, for example, in the following way. So you run this first part until it blocks on X1, and that means that it's now of this form and trying to receive a value. You suspend this, you don't actually run it quite yet. And then you pass this channel X2 to X1 with destination D, and when the function actually needs the argument, that will be a point of synchronization where you have to wake up this process and have it compute enough information that you can continue. So at this point, we have kind of combined functional programming, if you will, with a call by need or call by value or futures if you want to run things in parallel with the usual session type interpretation. Okay, so let me circle back now. So what is so special about the session types? So this is one, okay. I graded out because I didn't, like I said, I didn't really understand it yet. And then we have the substructural, which are linear affine types that reflect process state and evolve during communication. But we can put this in a larger context. We can revise and extend it, for example, to accommodate asynchronous communication, which requires continuation channels, which have suitable provenance. And then we have nonlinear types, because once you have asynchronous communication, it's relatively easy to add that. And then we combine them, and we can actually using that. So if you import this ordinary function of programming, what this translation gives you is what's called futures. So this is known since 1985. So you can have a sub-expression that you evaluate in parallel with the body of the function, and you only synchronize when you need that value. And that matches exactly what we're doing here. So I guess you could say that asynchronous session types is just a type system for futures. Okay? But we don't have to stop there. We can be a little bit more expansive. So, and then me and some collaborators have cannibalized the session types for mixed linear nonlinear types, which originally came from this problem. And then you can use it on the functional side to avoid garbage collection or reuse memory aggressively instead of having to deallocate it. And then the continuation channels that arise from the asynchronous communication actually give you a handle on how you might prescribe data layout in a functional language. Okay, so what I've learned here is, well, overall, first, the significance of linear types. Of course, I knew about them before, but I didn't fully appreciate them in the setting. Then the significance of mixing linear and nonlinear types. The elegance of futures, because they have a very clean, simple, elegant type system that's essentially just session types. And then also the connection between channel provenance and data layout. What I still don't know is fundamentally what are global session types. I've learned something here, okay, in the workshop so far. So I think I'm coming slightly closer to understanding that. And how they connect to local session types. And also what would global session types mean beyond just session typing? If you try to import these ideas to functional language, what would it be? Would it be something interesting? I don't know. Okay. So that's my last slide. Maybe this is a good slide to stop on because there's a lot of things I don't know. Okay. Okay.
Remember, you are using this language for education, right?
Yeah.
And this stateful session types, you need to write a lot of continuation. So how students feel? They manage to write a program without confusion, or they feel it's a bit difficult?
I can only tell you they manage to write programs. I don't know whether they can write them without confusion, okay? So because so when I taught a course previously and I didn't have an implementation, they had to write the code by hand and hand it in and grade it, and it was a sobering experience, okay? How do you grade a piece of code that doesn't even compile? Okay, so I decided to write an implementation, and now everybody got it right. Okay, so, but I don't know how often they iterated before they got it right. I don't know, but they were all able to learn that, and they're able to write like visitor pattern type things in object-oriented programming. So they were able to write quite sophisticated linearly typed code in the homework assignments. Okay, so having an implementation makes a huge difference because they get this instant feedback that allows them to see, oh, there, I'm telling them variable X is unused. What happened here? They can analyze it. So for example, I asked them, the very first thing I asked them to write conjunction on Booleans encoded as 1 + 1. And so they say, okay, well, if the first argument is false, I don't need to check the second. And of course, that's not linear, right? They get an error message saying it's not linear because you don't use the second argument. And so then they go and fix it, right? So I spent most of my time actually implementing error messages, okay? Which is probably a common experience for people who try to use these kind of things in education. But I can say, so far it's paid off, okay? So we'll see what happens in the second half of the course. So.
Okay, thank you very much. Very great, thank you.
Hi, nice talk. I have maybe a comment about your point one about the connection between global types and local types, the one you say you understand less.
Yeah.
I think what that means, what that represents is actually the connection with concurrency theory, and in particular the theory of process calculi, which were introduced with that distinguishing feature of being able to express both specifications written with what Milner called the dynamic operators, like plus and prefixing, which are syntax for LTSs, essentially, and which give you the sort of temporal dimension of a system, and implementations which are written with both these dynamic operators, but also the static operators, which are parallel composition, restriction, rename, or whatever, and which give you additionally also the spatial dimension of a system. So I think that kind of connection between a global sequential specification and sort of distributed implementation was already present from the very beginning in the theory of process calculi. And I think this is something new for maybe compared to classical type theory. And it comes from, for me, it comes from concurrency.
Yeah,
theory.
thank you. I think that makes sense. It also explains why I don't understand it. But I have learning to do. I'm always willing to and interested in learning more. And so one particularly interesting question, if I solve what the issue is here, if I can really understand the pi calculus, then what does it mean like for an ordinary functional language? Is there any meaning associated with that distinction? Because the closest I could think of is if you have a language with dependent types, you can express the specification and implementation in the same language. You erase all dependencies before you run it. But here, there's so much more going on that it didn't seem to be a good analogy. I think there's a lot more going on here than is going on in the traditional type theories. So yeah, I'm looking forward to understanding this better. And like I said, there were some talks today, and I talked to Jorge as well. I think I've already started making some progress on that.
There are no more questions. Let's say thank you again. This concludes our first day of ST30. People that were officially registered, have received an email to join dinner like a couple of weeks ago. We reached maximum capacity at the restaurant, so if you answered my email, let's just figure it out what to do for the next hour and 30 because the restaurant is scheduled for 7 p.m. So if you want to go grab a drink, in the meanwhile,